this model. And also, we would like to understand better concerning Zika and dengue. Dengue, now we have the vaccination, so it's better in some sense that we can avoid the dengue transmission. And but of course, we could also investigate more concerning the optimization of this vaccination. And in that case, again, it's really important to considering the incubation period of the mosquitoes, of the transmission. So it's really important to consider, even in the case that we have a vaccination, to considering these models with delays. So just to mention that usually in the epidemiology, it's very important to consider in this type of delay in the models. And now we are trying to think in other types of virus transmission in order to do better models for that, considering this time but incubation period. And we are now starting in Brazil some collaboration with Butantan Institute in order to see if we can work with them, because they have a lot of data, a lot of things that could help us to develop a better models, in the sense that we could avoid the virus transmission and avoid, like in the future, if we have some disease that could become some pandemic, so we could have a very good models in order to react very fast, as we made when we had the pandemics of COVID-19. So there are many open and developing problems in that field. So I would like to invite you all that if you are interested to collaborate with us in Unicamp, the State University of Campinas, my current university, we have a very big group of mathematical biology. So it is very interesting to think how we could improve the models, putting more realistic variables, let's say also stochastic work with that, because we know that all of these models usually are not deterministic, but also depends on some probability. And it's also important to try to improve even more in order to have a more reality for the disease and for the models. So that's our work. And just before finishing, I would like to advertise two conferences that we will have. So now we will have in Argentina a joint meeting, Argentina and Brazil joint meeting in mathematics, and we'll be in Mar del Plata in September. And I would like to invite everyone that are interested. This is a joint conference between the Argentina Mathematical Union and the Brazilian Mathematical Society. So it will be the first edition, and it will be very nice. Very, very excited about that. And also, I would like to advertise also this one, that's the Clank-Umalka Conference in Mathematics. This is a joint conference with a center in China for the Latin American mathematicians that was created. And Umalka signed an agreement with this center. And now every year there will be a conference of Clank-Umalka, one in Latin America and the other year in China. So this one will be in this last week of August in Campinas, and I would like to invite you all. We are planning some advanced schools for the younger researchers, for the PhD students, so you all are invited. And yeah, so it would be very nice to host you all in this conference. So thank you very much again for the opportunity, and I am very happy to participate in this conference. ICMAM, as I mentioned, has been a very great partner of Umalka, with many joint activities together, and especially Duvan Carona has been a very good partner of Umalka in all our activities. So thank you very much.
Thank you, Professor Jacqueline. Thank you for your very interesting presentation and for accepting our invitation. Are there any questions in the public? Remember, you can write them in the chat or raise your hand. Yes, Cabe.
Uh, can you hear me?
Yeah, yeah.
Thank you very much for your very insightful talk. I have learned a lot about many new things. Something that in particular is interesting for me is about cancer. I wanted to ask at what stage is the research in cancer, and can you advise some references to learn about more about PD and cancer?
Yeah, there are some results in that direction, but few of them brings together like models that have delay equations. So I would recommend, and there is a PhD thesis that was defended in Germany that's from Maria Barbarossa, and she has one chapter that brings a lot of concerning the advances in these models for the cancer cells proliferation, and also mentioned concerning to add the delay, state-dependent delays on those models. So I think it would be very interesting to read that and to see, because she brings a little concerning the state of art of these type of models. But I know that there are very few works in the direction of state-dependent delays. Also, just to mention, there is a very important group working on that in Szeged, in Hungary. There is one group, very Gergely Host. He has several works in that directions, also concerning mathematical biology, cancer cells, and he works with PDEs and also some delays. So it would be very nice also to see, to read some works of him, because I believe that also you could be more updated concerning the state of art of these models. But I'm very glad to hear that you are interested about this topic. I think it's very interesting.
Yeah, so well, the reason for this is my brother, he's working on cancer, but he's not mathematician, but he's interested. So I was thinking maybe it will be helpful to, as he is working on cancer, to we can have some joint work on cancer. So maybe I didn't remember what you said about the references. Maybe I could write to you email and
Yeah, sure.
email you. Uh,
Yeah, surely,
Thank
surely.
you.
You are welcome. And for sure, I think it's really important when we do like some mathematical biology to work with people that's also understanding concerning the main topic, let's say, the biologists. That's why we are trying to strengthen our relation with some institutes in Brazil, like Butantan Institute, also Fiocruz, because we have some specialists that understand very well the behavior of the virus, the disease, and to put everything in the model, and brings more reality for that. So I think you are going to the very right way, let's say, working with some specialists in cancer, and then to in order to develop a good model. Yeah, and for sure you can be free to write me. It will be a pleasure.
Thank you very much. Thank you, very, very good. I will write you later. Thank you very much.
Okay, thank you.
Thank you. Thank you, Professor Jacqueline. In the chat, they are asking, how did you estimate the parameters for the model?
We in our model specifically, we use data, and we use the data from Fiocruz and the SUS in Brazil. So based on that data, we could estimate the parameters that appear in our model in order to do the simulations. Yeah, so we use the data. Yeah,
Thank you very much, Professor Jacqueline. Are there
thank you.
any other questions?
Okay, maybe I can mention something. It's not a question, it's not a mathematical question, but it's maybe a comment to highlight the talk of Professor Jacqueline Mesquita. At ICMAM Latin America, we are very grateful with you because you support us even 2 years ago when we meet in Germany in a conference of Enrique Suazua. After that, you have been very supportive to ICMAM conferences and in starting cooperation with us. And just, I think for young mathematicians, it's very inspiring to hear a talk by a woman mathematician, right? And actually that is doing applied mathematics, as you can see in her talk. So that's very nice. This is maybe first comment, and maybe second comment, more related with the, maybe if I can share a screen, the activities of Humalca on behalf of Jacqueline, right? Because after the presidency of Jacqueline, Humalca have become to be a very, very, very active society, as you heard from her, right? I really invite to the ICMAM community also to visit the website of Humalca to see all the things that Jacqueline is leading in our region, right? For instance, you have there the journal Orbita Mathematic, which is very nice journal, a new journal, right? Newsletter of Fumalca actually was an initiative that Jacqueline start. I also could mention the seminar Orbita Mathematica, right? That started recently. I encourage people, especially people here from ICMAM community, to join these activities because this is a very good effort from Jacqueline, and of course, our joint activity between Tumalca and ICMAM Latin America, which is the seminar, the Latin American Seminar of Mathematics, where, for instance, Manuel here is organizer, and you will see the next talk will be by Mariel Sainz. So maybe just this is a short comment making information, just informing people about activities of Humalca, and of course, expressing to Jacqueline our gratitude from ICMAM for all the support this last period, this last year, especially. So thank you, Jacqueline.
Thank you, Duvan. Thank you very much for this advertisement. Yeah, and it's a great pleasure to us to collaborating, collaboration with ICMAN. Yeah, thank you very much for all the support that also you are doing to Humalca. Thank you.
Oh, Manuel, maybe you can continue, please, with the sharing duties.
Thank you. Is Professor Dong Hyun Cho in the room with us? Yes, I can see you are here. Good morning, Professor. Good afternoon. Would you please try to to share your screen?
Excuse me, can I stay here?
We can hear you.
Yeah, I'm ready.
Okay, please try to share your screen, Professor.
Okay.
Thank you very much, Professor. Thank you for each and every one of you for joining this presentation by Professor Dong Hyun Cho, to whom we are very grateful by his contribution. He is from Kyung University, and his presentation is titled an analytic Feynman integral over paths. Thank you, Professor, for joining us today. The time is yours.
Okay. Okay, thank you very much. First of all, I really appreciate to give me a chance to talk about my topic, Feynman integral and Brownian motion and their related topics. So at first, Feynman integral was introduced in 1984, and this integral has had a major influence in several areas of mathematics and mathematical physics. There are many approaches to the Feynman integral, but in my case, the approach is the analytic continuation from the Wiener integral on classical Wiener space. This space is the space of continuous real-valued functions which vanish at zero. So today's topic is the analytic Feynman integral over passes, which is related to the Brownian motion. And actually, this approach is to solve an integral equation, which is formally equivalent to the Schrödinger partial differential equation. So I would like to give a talk like this first. I introduce an analog of Wiener space with a scale factor. This is our underlying space. And then we introduce a stochastic inner product with its probabilistic property. This is related to the Brownian motion and normal distribution. And then I'll give evaluation formulas and examples like this. First, I will introduce a Banach algebra over passes in abstract Wiener space, which is an analog of Wiener space. And then on the Banach algebra, we evaluate L and analytic Feynman integrals using the analytic continuation. And then we will give several examples. So we need underlying ideological basic space, which is called abstract Wiener space. So first we need infinite dimensional real separable Hilbert space. We denote this space as H. And then we can take an infinite dimensional real separable Banach space, which is denoted by B, and then we can obtain this relation. This space means dual space, and then we denote this notation. We use this notation as an inner product on the Hilbert space, and the norm like this, and then this notation used as a dual pairing between the abstract Banach space B and B star. This is dual space, the Banach space, with the norm like this. And then actually this is equal to Hilbert norm. And then this triple is called abstract Wiener space. Abstract Wiener space. And then this is Banach abstract Wiener space. This is a border class of abstract Wiener space, and this is a probability measure which is similar to the multivariate normal distribution. And then actually in classical Wiener space, every Wiener path which is Brownian particle, but this path every path starts at origin, actually zero. But in my case, the Brownian particle need not to start origin. And then I will give a finite measure on the initial distribution. This is, actually, this is not probability measure. And then for positive law, we denote two kinds of measure like this. Actually, this is scaling of the abstract linear measure and this measure. And then this is our space, our underlying space, which is the space of abstract linear space value, the continuous functions on the interval 0t, and then we introduce a strictly increasing function like beta like this. Actually, this is variance function of the Brownian motion. And then we give to give a pre-measure on analog linear space this, and we need two kind of function like this. So this is a partition of integral 0t, and then we can define two type of function t and j like this. This is the definition of the function t. This is the definition of function j. Actually, this function is called a kind of cylinder function. So, we need to define analog linear measure on this space. We need an algebra. So for border set in the product of abstract linear space. So we need the pre-image of this border sets, and then this is called an interval. And we give a pre-image on interval by like this. And then actually this pre-measure is countably additive on the class of intervals, and then the border sigma algebra of the analog linear space with the supremum norm coincide with the smallest sigma algebra generated by the intervals. And that actually, I give the proof on another paper. So, and then there exists unique positive finite measure like this, which extend the pre-measure on the intervals. And then this measure is called the generalized analog linear measure on the analog linear space with parameter law of passes in abstract linear space according to beta and the measure phi. Actually, this measure is not this measure is not to a probability measure, but if the initial distribution is probability measure, and then this is probability measure. In this case, this measure pi need not be an abstract linear measure. If we take law as a unit and beta is identity function and pi is Dirac measure, which is the case, the classical linear space, and then the analog linear space reduced to the measure, the special measure, which is introduced by Professor Yu. This is the reference is provide the list of references, and then we define this kind of stochastic process, which is called generally Wiener process, which is the kind of Brownian motion. And then actually this measure is a probability measure, and then this is a vector valued stochastic process. Actually, this is a generalized Wiener space, the generalized Wiener process, but actually not exactly Wiener process, because this is not the probability measure. Now, we introduce using the display measure, and then we can derive this kind of generalized Wiener integral formula, which is proved in another paper. So let f be function defined on the product of abstract Wiener space, and then this function small f is a border measurable on the product the product of Wiener space, abstract Wiener space, if and only if this composite function, this is Schlittner function, this is composite function is border measure on the analog Wiener space. If one of these conditions is held, and then we can obtain this kind of integral formula. Here, star equality means that once either side exists, then both sides exist and they are equal. Now we introduce a distribution of generalized Wiener space. If this function xt defined on abstract Wiener space, analog Wiener space to abstract Wiener space, like this, and then this notation, this symbol denotes the image measure induced by this process, and then we can obtain this kind of distribution. Actually, this is not the probability measure, because this is the initial distribution is not a probability measure. And then actually most of measure space, almost every concept is very important, but in our cases, they don't roll in Wiener measure theory. So we need another measurability like this. Actually, this is called scale invariant null measurable M, and scale invariant null set like this. If a set N is called scale invariant null set if every scaling of the set of measure is zero for any positive law. And also, a practice set to hold S almost everywhere. That means S scale invariant almost everywhere. If the measure is a probability measure, we can say generally scale invariant almost surely if it holds except for scale invariant null set on the border class of the abstract Wiener space. And then this is scale invariant null set, the concept of scale invariant null set and S almost everywhere are understood on analog Wiener space. So similarly, this is concept on abstract Wiener space. This concept extended to analog Wiener space with this measure. Actually, the scale invariant measurability is an equivalence relation on the set of border measurable functions on analog Wiener space. This is important in our theory. Now we define analytic integral and analytic Feynman integral on analog Wiener space. So we need two kinds of set, which is a subset of complex numbers. C plus T naught, the set of all complex numbers is positive real part. This means the light have complex plane. And then we add the imaginary axis, and then we can use this notation. So this is the set of all complex numbers with non-negative real parts. And then to define analytic Wiener integral, we need a scale invariant measurable function on the analog Wiener space. So first, we assume that this function is integral over the analog Wiener space, and then we adopt this kind of notation, and then if this integral has an analytic extension on the light have complex plane, and then we write like this. This means a generalized expectation of analytic Wiener integral of f. And then we call this extension, analytic extension, called generalized L1 analytic Wiener integral of f with a parameter lambda. If the analytic Wiener integral of f has a limit on the light have complex plane. This is a non-zero real of Q. This and then this limit exists, and then this we write like this, and the limit of this limit is called the analytic L1. The generalized L1 analytic Feynman integral of f with the parameter Q. Actually, this Q means mass in Schrödinger partial differential equation. And also, we need this kind of square root. Actually, the square root of lambda, in this case, lambda is complex number, and then we have two kinds of square root, but we will understand that this square root as a square root of lambda with non-negative real part, because we use light have complex plane. And also, now we introduce a stochastic inner product, which is used to derive the distribution of Brownian motion. So we take this kind of set, which is a complete orthonormal subset of Hilbert space, which are the dual space of abstract Wiener space. And then we can define the stochastic inner product on the abstract Wiener space like this. Actually, this is two possible identity, but not exactly possible identity, because this is the dual pairing. Actually, this limit exists almost every sense, and that, but we define if this limit does not exist, and then we can define this stochastic inner product as a 0. Here is a remark to the stochastic inner product. So actually, there are many complete orthonormal subset of H. So, but this definition, the stochastic inner product is essentially independent of the choice of complete orthonormal subset used in its definition. this is not independence in random variable. Only it is no relation to choice of the choice of complete orthonormal set. And also, this stochastic inner product has it is a random variable which is normally distributed. This means Gaussian with mean 0 and variance is the Hilbert norm of H. And then we can find this kind of formula. Actually, this is equal to almost this limit as for almost everywhere sense. This is abstract unit measure. Actually, this x1 belongs to the abstract unit space, but in particular, this x1 belongs to Hilbert space, and then this stochastic inner product equals to the inner product on the Hilbert space by Pascal's identity and this identity. And then these two random stochastic inner product has a Gaussian distribution. So we need the covariance of these two stochastic inner product. But actually actually the covariance is the scaling of scale and the inner product of this H1, H2. So these two stochastic processes, which are random variables, are independent if and only if the H1, H2 are also orthogonal in the Hilbert space H, because two stochastic processes are Gaussian. So we need only to introduce the independence of random variables. We need only the covariance of the random variables equals to 0. So this is two equivalent conditions because of the Gaussian. So we introduce the properties of this stochastic processor. We need some notation like this. This ML denote, as you know, this notation ML is the log measured on the real line, and then this is a dot product on the n-dimensional Euclidean space, and then this vector is an element of the n-dimensional Euclidean space, and then actually U is a low vector, A is n-dimensional scale matrix, and then this is not defined, but this notation is matrix multiplication like this. So we we introduce joint distribution of the stochastic inner product. So this denotes the random joint random vector, and then and also and X low is this joint random vector, and also this matrix denotes the inner product with the scaling low scale, and then distribution is Gaussian. So this distribution to Gaussian. But actually, this H, actually this is did not be independent vector, independent in the Hilbert space. So this we can admit the joint Gaussian can be degenerated, but this H is linearly independent, and then this matrix is positive definite and invertible. So the inverse of this matrix is positive definite. In this case, this random vector has a density function because this is the invertible matrix. So that this kind of density function, joint density function, and then this matrix is actually covariance matrix of this joint distribution. In this case, this random vector is non-degenerate multivariate Gaussian distribution. Mean vector is 0, and then covariance matrix is like this. So with the same condition, this is a linearly independent set, and then we can kind of we can obtain this kind of equality. So actually, a small f is defined on the n-dimensional Euclidean space, and then this function small f is Borel measurable on the Euclidean space if and only if this capacity function is a Borel measurable on the abstract Venus space. If one of these conditions is satisfied, and then we can obtain this kind of integral formula. Actually, this is similar to Wiener integral formula. This means exactly this x law is distributed by multivariate Gaussian. And then actually this set is an orthogonal, and then this formula is reduced to the covariance matrix is diagonal matrix. So we can this formula is reduced to this formula. This is important in the theory of Brownian motion and Wiener space. Actually, as you know, the stochastic inner product is independent if and two stochastic stochastic inner products are independent if and only if orthogonal. H1 and H2 are orthogonal, but actually there are three kinds of equivalence. This is orthogonal subset of Hilbert space if and only if this stochastic inner products are independent random variables, which means every finite choice of this stochastic inner product are independent. Is generally that's a independent in random variables, but actually this is equivalent to pairwise independent random variables in abstract unit space. So we can this is to verify easy. So we sometimes we use this kind of independence. Now we give analytic Feynman integral, so we need a Banach algebra. T is like this. The interval belongs to interval A, B, like this, and then this symbol denotes the class of all complex values Borel measures on the Hilbert space with the bounded variation, and then we can define this kind of set is the space or scale almost every equivalence class of functions on the analog unit space which have this kind of form for actually this is defined on scale invariant sense. And then this space is actually Banach algebra over complex, the set of complex under pointwise addition, pointwise multiplication, complex scalar multiplication. And then actually the product is actually the convolution of this kind of function, but the convolution of this measure, which corresponds to the product of this function. Actually, if we define the norm of this function is defined the norm of the total variation of the measure, and then we can obtain a Banach algebra, and also this is actually this is just equivalence class, but there is no relation to the choice of the measures. So this norm is well defined. Actually, I proved this theorem on some paper. Now we define Schlinger function on this. For this function, we will evaluate the analytic Feynman integral. So, still, this is a subset of Hilbert space, but in this case, this is also normal subset of Hilbert space, and then this space denotes the set of all Schlinger functions like this. Actually, so this function Fr belongs to LP space, but this is equivalence class, not one function. So we can establish the well-defined the Schlinger function because this is a member of equivalence class in LP space. So without the loss of generality, we can take Fr to be Borel measurable on the Euclidean space. You note that every element of LP space equivalence class of functions rather than a function on Euclidean space. So one can show that for the function Fr Fg on Euclid defined on Euclidean space, and then these two functions are equal for almost everywhere, and then this two Schlinger function is equal in the sense of scale almost everywhere everywhere on the analog unit space. Now, to evaluate analytic Feynman integral, we introduce some notations. This is Hilbert. This is inner product. This is vector of the inner product, and then we adopted the psi t function, which is actually general normal density, and then we can obtain the analytic Feynman L1 analytic Feynman integral of the product of function which belongs to Banach algebra and cylinder function, and then we can obtain this kind of analytic Feynman integral of the function, the product of this function. This kind of actually the calculation is very complex, and then the cylinder function fr belongs to L1, and then we can obtain the analytic Feynman integral of the product of this function, and the form is C0. It is given by the right-hand side of the equality just stated, which means this equation replacing lambda with minus IQ. Still, Q means mass in Brownian motion. Actually, the quantum mechanics. Now we introduce Fourier transform measure on the Euclidean space. So this space is the space of all complex Borel measures on Euclidean space. And also, this is the Fourier transform of this measure. And then we can define the cylinder function like this using the Fourier transform, and then we can obtain the product of Fourier transform and the function belongs to Banach algebra. The function of the analytic Feynman integral of this function is given by like this, and also the analytic Wiener integral. This is the analytic Feynman integral, which is given by this equation replacing lambda with minus I. This Feynman integral is already exists for this kind of cylinder function. Now we introduce some examples using previous evaluation. Still, this function belongs to the Banach algebra, and if the measure is defined on Euclidean space is particularly especially multivariate standard normal distribution, and then we can obtain this kind of analytic Wiener integral and analytic Feynman integral like this. Also, the calculations are very complex in my case. And then here are another example. If we adopt the measure on complex measure on Euclidean space replaced by Dirac measure, which is constant at origin, and then we can obtain the analytic Wiener and Feynman integral of the function belongs to the Banach algebra is like this. It's like this. We can take this kind of equation, and then we can obtain this kind of analytic Wiener and Feynman integral from this formula. And then we can also obtain the analytic Wiener integral of the cylinder function is as like this, because in this case we take the measure sigma as a Dirac measure at the 0, and then we can obtain this kind of analytic linear integral of the cylinder function. And then actually there are two kinds of this equation, because this function is L1 belongs to L1, and then we can do analytic Feynman integral of the cylinder function. The formula is given by this equation replacing lambda minus IQ. And also, if this cylinder function is a constant function, and then we can obtain this kind of formula. Actually, this is the constant function. This is normal density. So we obtain this kind of equalities. Actually, this initial distribution is not the probability measure. So we can obtain this kind of formula, which is the constant C product the measure. This is a kind of scaling. Now we can obtain the analytic linear integral of the cylinder function, which is defined on the Fourier transform, and then we can obtain this kind of analytic linear integral and analytic Feynman integral, and also this is a normal distribution. This is normal distribution, and then we can obtain this type of analytic Feynman integral, because from this formula, from this formula, and then this is all one. So this integral is all one. This integral is one. So we can obtain this equation. So this measure is multivariate standard normal distribution, and then we can obtain this kind of analytic linear integral and Feynman integral. In this case, lambda is replaced by minus IQ. Still, this Q means non-zero real number. Actually, non-zero real number, non-zero real number and positive. So this Q is still the mass in Brownian particle in the Brownian motion. So here are some references related to my topics. This Professor Cameron was died, I think 1919, I forget the exact year. So this is still references related to my topic. This is the original paper, the space-time approach to non-relativistic quantum mechanics. In this paper, the concept of Feynman integral is introduced, but Richard Feynman does not give an exact definition of the Feynman integral. So there are many Feynman integrals. In our cases, the approach is using analytic continuation on the light complex plane. Another approach to the Feynman integral is to use limit of sequence, but the calculus is very complex. So most of researchers does not approach to the sequential Feynman integral. and also one of researchers approach to the primary integral using path integral, but in their case, they do not use or does not use measure. They use only diagonal function, polynomial function and the continuous path, because they divide the continuous function, divide line segment to line segment finitely, and then they use the limit to approach the continuous path, which is the path of the Brownian particle. So this is another references. This reference is important to the abstract Venus space. Most of abstract Venus measure theory are appeared in this book. This is not paper, this is book. Okay. Professor Yu is introduced generalized analog Venus measure, but this is our case is the generalization of the measure introduced by Professor Yu. Also, this is an important book in linear integral theory. This is like a Bible in our theory. Okay, thank you very much. Let me stop.
Thank you, Professor, for your very insightful and interesting presentation. Thank you again for participating in this conference. Now the space is open for questions. Please feel free to write them in the chat or raise your hand to ask a question. Oh, okay. While the attendees think about their questions, I would like to ask you about the Wiener processes. I believe I understand they are very related to Brownian motion. I don't know if they are also related in your work. Could you perhaps tell us more about it?
You mean more my research? Your question is, sorry, I can't understand your question.
Okay. I was asking about Brownian motion. I understand they are related with Wiener processes.
Yeah.
Could you perhaps tell us more about it?
The Wiener process is actually a kind of Brownian motion.
Okay.
Wiener process describe the behavior of Brownian particle, and also actually I interested in conditional Wiener integral. That means particular path belongs to a particular time. The path belongs to a particular point, and then that's the conditional Wiener integral. Because we can give exact probability of the path, but only we can give the Wiener measure on the interval which the path belongs to the interval. So we need probability. But most of researchers in this our field are use normal Gaussian distribution. And also I still study the this is small work in my theory, but actually I study conditional Wiener integral on more generalized space.
Okay. Thank you very much, Professor. Are there any other questions? Yes, Duan, please.
Sorry,
Sure.
because our field have small researcher. So now most of all the research are retired. So I think we are last generation of this field.
Okay. Okay.
Sorry.
I see. It's very interesting, of course. I have a question about the definition that you have of a stochastic inner product, right?
Yeah.
A stochastic inner product. If you could you please share your presentation and maybe
Yeah. This is you mean I think
when you define a stochastic,
stochastic inner product. You mean stochastic inner product?
right, in the definition, because I have a question maybe related with the
So excuse me. Yeah.
with the geometry that this
Definition. Yeah.
my question is related with the geometry that is induced by this inner product compared with the setting of Hilbert spaces, right? Because for instance, if you take one vector H, which is non-trivial in a Hilbert space, and you define let's say the orthogonal space to that vector, you are going to have one subspace which has codimension 1, right?
Yeah.
But my question is if how much the situation is different in this case. Let's say one wants to study, let's say the subspace that is orthogonal to one non-trivial vector, but with respect to this stochastic inner product, if you have a notion of codimension associated to it, or how is the intuition with respect to the standard definition of inner products on Hilbert spaces?
I think your question is very, I think, to understand. If you mean if this is absolute unit space, this is Hilbert space, and then this kind of inequality, this inclusion, this is this is Hilbert space. This is this type, and then we can obtain this kind of inclusion. So the dual space, the abstract unit space is belongs to Hilbert space, because this Hilbert space is always self-dual. So
right, but B is Banach space, right?
Yeah.
B is Banach space.
Yeah.
So my question is how much the notion of, let's say, orthogonality is different from the one from Hilbert spaces, right?
Yeah, but actually, this space is measure zero, unit measure zero, the Hilbert spaces. Sorry, this is. Sorry.
Or if you allow me,
this is the probability space. This is unit measure. This is the probability measure. In the sense of the measure mu have this is abstract measure, but the measure mu measure of H is zero. So this is larger than H, and also this is Hilbert space. This is only Banach space, not Hilbert space, right. And also Hilbert space, and also
right.
This is kind of functional analysis. This is reproducing kernel Hilbert space of the abstract unit space. This means in.
But I understand H Hilbert space, but in your analysis, B is Banach space or is Hilbert space? V.
Yeah. V is not Hilbert space.
It's Banach space, right? So could you please go to right? So could you please go to the definition of a stochastic inner product?
Stochastic use probability use random variable. So,
Okay.
so
Okay.
your stochastic actually this limit is this limit is actually
Right. Yeah.
this limit is actually using the convergence of random variable
Right.
on yeah.
So Professor Cho, I think your talk has been very nice, of course. You have given us a lot of intuition about the stochastic analysis. But my question is more concentrated, let's say, if for the definition of a stochastic inner product, right? Let's say you fit X1, right? You fit X1, and you want to see what is the kernel of the functional that you define, right? Which will be the inner product of any edge vector of your Hilbert space with respect to X1.
Yeah.
Who is the kernel of this functional? I mean, it has the structure of let's say, has in Hilbert spaces of a subspace that has codimension 1, or maybe, I don't know, maybe the geometry is different. Is different to the one of Hilbert spaces. That was my curiosity. But just a curiosity. I mean, I don't know if I have formulated well the question.
Sorry,
Okay.
I can't understand your question exactly.
Okay, I think then maybe I will write you an email with more details. Better.
Actually, this is this stochastic inner product introduced in this reference. In this
transactions.
Sorry. In column, this reference. I adopt this definition on this reference. Generally, we use stochastic inner product in this book. I think in this book we adopt stochastic inner product. But
Thank
actually,
you very much.
that inner product is identical concept of the limit of random variables on the limit of random variables on Gaussian space.
Okay.
Yeah.
Thank you very much. Thank you very much. Thank you.
Thank you very much, Professor. Thank you again for joining us in this conference and giving this very, very interesting presentation. Now I'm gonna give the space to Fred.
Thank you, Manuel. Thank you, Manuel. So our next speaker is Suleimanov. So please, could you share your screen with us before we do the proper introduction?
Thank you very much. Can you draw my presentation?
Yeah, can you make it full screen? Yes. So our next speaker is Professor Suleimanov. Professor, we are very happy for having our invitation. The professor is going to present on the title New Properties of Maxillary Function and Their Application. Professor, the floor is yours, so you may proceed.
Thank you very much. Hello, everyone. Today I am going to present my work entitled New Properties of Symmetrical Functions and Their Applications. In this talk, we studied several new properties of symmetric Leffler function and discuss their applications to fractional differential equations. Let me briefly describe the main focus of this report. Firstly, we investigate new properties of symmetric Leffler functions. In particular, the monotonicity of symmetric Leffler functions with respect to the parameter rho in two cases. The first case is monotonicity with respect to the parameter rho for large arguments. Second case is monotonicity with respect to the parameter rho for small arguments. Then we apply these results to the inverse problems for fractional differential equations. Let me begin with a brief introduction. The Mittag-Leffler function plays a central role in fractional calculus and fractional differential equations. Its main analytical properties, such as asymptotic behavior, positivity, and complete monotonicity with argument, have been extensively studied. In addition, you can also find more properties of symmetric Leffler function in this monograph. Up to now, most studies have focused on monotonicity with respect to the argument t. In particular, the exact values of rho, the functions are monotone, decreasing, or even completely monotone on this interval. However, the dependence of symmetric Leffler function on the fractional parameter rho has remained largely unexplored until recently. The first results in this direction were obtained in the works of Professor Alimov and Ashurov in this article. The study of the monotonicity of symmetric Leffler function with respect to rho is essential for the inverse problems, namely if the fractional order unknown, then we use these monotonicity properties of symmetric Leffler function to find this unknown fractional order with additional data. In such problems, monotonicity is a key tool for establishing uniqueness, existence, and stability. In this talk, we investigate monotonicity properties of symmetric functions with respect to the parameter rho and discuss their applications to inverse problems. Recall the symmetric function defined by the following series and generalized to the two-parameter Mittag-Leffler function is defined as follows. Let me note an important special case. If the parameter rho is equal to 1, then the Mittag-Leffler function reduces to the classical exponential function. Now we study the monotonicity of symmetric Leffler functions. Leffler functions. The following two theorems obtained in these articles. The first theorem, let rho 0 between 0 and 1 and lambda 0 be positive. Then there exists a number t0 such that for all t0 and lambda, the function is positive and monotonically decreasing with respect to rho. Similarly, theorem 2 shows that under the same conditions, the function are positive and monotonically decreasing in this interval. Now I will explain the main idea of this of the proof. We introduce the spatial contour in the complex plane denoted by delta. This contour consists of three parts. Two rays with arguments minus beta and beta, and an arc of the unit circle connecting them. This contour divides the complex plane into two regions denoted by G plus and G minus. Such a contour is known as the Hankel path. Using this contour, we can write the integral representation of symmetric Leffler function as follows. Now, for proof the above theorems, it's sufficient to prove that this derivative if the derivative is negative, then the integral function is monotonically decreasing, and this derivative is positive, then the integral function is monotonically increasing. In above works, namely Professor Aliyev and Ashur's works, the derivative showed that is negative. Therefore, the second proof the integral function is monotonically decreasing in the interval. Using the above method, to prove that the monotonicity of symmetric Leffler function with respect to rho, we had to assume that T is sufficiently large. In this section, we propose a different method that allows us to obtain similar result for small values of T. Now I will give the main results. Let rho 0 between 0 and 1, then for any T, the integral Leffler function is monotonically decreasing with respect to rho. Next theorem, let rho 0 between 0 and 1, then for any T, the function is monotonically decreasing with respect to rho. These theorems obtained in this work. To prove these theorems, we used some ideas from this paper. In that paper, the authors proved the derivative of this function is negative if T is large enough and C is small enough. Now we will give proof of theorem 3. For this, we calculate the derivative of the integral Leffler function. For this, we use the gamma function, which is logarithmic derivative of the gamma function. Using this equality, we have the following equality. For proof this theorem, we also use the following lemmas. Let rho between 0 and 1, then the following limit holds. Also for rho, the following two statements hold. The proof of lemma is technical, but essential. It based on a two-sided estimate of the ratio, and one can show that both bounds 10 to 1 as n goes to infinity. Now we give this lemma, let rho 0 between 0 and 1 and t0 is positive. Then this series 2 is absolutely and uniformly convergent with respect to rho and t. The idea of the proof is as follows. By taking absolute values and using the bounds t and rho, we can estimate each term by this follow this. Then we consider the following ratio, and we using these equalities, we have the following expression. Using the above lemmas, we have this equality. Therefore, we conclude that the series is convergent. Then, by the Weierstrass test, we deduce that the series 2 is uniformly and absolutely convergent. Now we prove the following lemma. Let rho between 0 and 1, then for t, the following inequality holds for all n. For this, we consider the following ratio. Using this equality, we have the following expression. Now we will show that this absolute value of this ratio less than 1. For this, we can rewrite the gamma function as follows. And we get the following estimate. From this, according to this statement, we have the following estimate. If we choose logarithm t this form, then we have the following inequality. Using this inequality, we obtain the following expression. In order for this ratio to be less than 1, we require this expression less than 1. From this inequality, it follows that t less than this expression. Therefore, if we select t as follows, then we have this inequality. For such t, according to assertion 2 of lemma 2, the sequence yn defined by the equality 3 is negative for all n. Therefore, we get the following inequality. From this, we prove the main theorem that according to lemma 3, the series 2 converges absolutely. Therefore, we can divide this series into groups as follows. Then by lemma 4, it follows that this derivative is positive for all t and rho. Similarly, the proof of theorem 4 similarly proved as theorem 3. Now we will show that these properties of symmetrical function apply to inverse problems. When considering fractional differential equations as a model, the order of fractional derivative is often unknown and difficult to directly measure. To find this parameter analytically, we come to consider the inverse problem of identifying the order of fractional derivative. Let us consider this inverse problem using the following simple initial boundary value problem as an example. This problem also called a forward problem. Here, tilde is the Laplace operator, and T alpha is Riemann-Leibniz fractional derivative of order alpha is defined as additionally this is the Caputo fractional derivative. Now we consider several literature of these inverse problems. In last decades, this type of inverse problems has been actively studied by many specialists. A number of interesting results have been obtained. In inverse problems, the choice of the overdetermination condition occupies an important place. The authors mainly use the following overdetermination condition. Using this overdetermination condition, the authors proved only uniqueness of the inverse problem, of the solution of the inverse problem. Then Professor Alimov and Ashurov use this following overdetermination condition, and they can prove that the existence and uniqueness of the solution of the inverse problem. For this, it is to use the monotonicity of the Mittag-Leffler functions. Now we consider the following inverse problem. It is this is Riemann-Leibniz fractional derivative. This is Neumann boundary condition, and this is our determination condition. For solving this inverse problem, we prove the following lemma. Let rho 0 between 0 and 1, then there exists a number t0 such that for all t and for arbitrary phi, function f is monotonically decreasing with respect to rho. From lemma, the author proves the following theorem. Let t0 more than satisfying the following this inequality, then the inverse problem has a unique solution if and only if this inequality holds. Solution of a forward problem has the form, and using the overdetermination condition, we have the following function. Prove the lemma is reduced to the study of the monotonicity of this function. Using the above theorem 2 and lemma 5 is proved. Now, using theorem 4, we also prove the following theorem. Let rho 0 between 0 and 1 and t between this in this interval. Then the inverse problem has a unique solution if and only if the following inequality holds. Similar the inverse problem considered with the Caputo fractional derivative. The solution of the with Caputo fractional derivative with discrete boundary condition. This solution of the forward problem as follows. Then using above our determination condition, we have the following expression. for this function f is monotonically decreasing. For proof this, we use theorem 1, which is the monotonicity of symmetric Laffer function with respect to rho. Additionally, using theorem 3, we have similar results in this case. Now we consider second inverse problem. In 2013, Tatar and Ulusoy studied a two-parameter inverse problem for the fractional differential equation with the Dirichlet boundary condition. They assumed that the initial function X is smooth and all of the Fourier coefficients is non-negative. The authors proved only uniqueness with the following over determination, with use the following over determination condition. Next, in 2020, the Professor Yamamoto extends the uniqueness result to an n-dimensional bounded domain omega with smooth boundary. And the assumptions are less restrictive in this form. Under the over-determination condition, the authors also proved only uniqueness of the solution of the inverse problem, two-parameter inverse problem. In word, we consider the following two-parameter inverse problem, and using the following over-determination condition. This over-determination condition and the formula for the solution of the Fourier problem, we have the following system of equations. This system of equations prove with the monotonicity of the symmetric function with respect to rho and sigma. And let us introduce the following notation. Now we give main theorem. Let lambda k0 more than 1. Then there exists a positive number T1, such that for all T1 and T2, the two-parameter inverse problem has a unique solution if and only if this point belongs to the range of the function f. Now we consider next inverse problem. Recently, this author considered the following inverse problem. The following inverse problem, it's really interesting because of the over-determination condition given at a single space-time point. The authors proved that if omega is the domain and the eigenfunctions satisfying the certain conditions, additionally, the diffusion coefficient is sufficiently small and the measurement time T0 is sufficiently large. Then this function is strictly monotonically decreasing on rho. And the inverse problem has a unique solution. However, these conditions are not sufficient in general. Counterexamples can be constructed. Using, the authors proved several auxiliary lemmas which are undoubtedly of independent interest. Using some ideas of this article, we proved the following results. Firstly, removing the smallest restriction on C, and removing the restriction on the dimension D. Additionally, providing a complete version of the monotonicity theorem. Now, firstly, we introduce some notations. Let A be a self-adjoint extension of the Laplace operator with the homogeneous Dirichlet condition. Let Vk and be the eigenfunctions and lambda k the corresponding eigenvalues of this operator. For any real tau, define the fractional power of A as follows with domain, with the following domain. Definition, for a fixed M, we will say that F belongs to this class if the following, if F satisfies the following conditions. Now we will give the result. Recall that the authors consider the following inner problem. It's not hard to prove that if P belongs to this class, then this function, the solution of the forward problem. Now we will give the following lemma. Let rho 0 between 0 and 1, and T1 is positive. Then for any number epsilon, there exists n0 such that the following equals false for all x and phi. Using above lemma, we will present the theorem about the solution of the inverse problem. Let epsilon be a fixed positive number and t between t belongs to this interval. Denoted by n0, the integer defined in the lemma 6. Suppose that for some fixed point x0 and for some quantities of vk and vk satisfies the following two conditions. Then the nonlinear function is strictly monotonically increasing on the interval. Moreover, the inverse problem admits a unique solution if and only if D0 belongs to this interval. To prove this theorem, we use theorem 3, which is monotonous of symmetric Lefler function with respect to rho for small argument t. Now we present the results of Psu, Professor Psu. An interesting result by Professor Psu published in 2002, which, as far as we know, represents the first inverse problem for determining the order of fractional derivatives. Consider the equation where the x rho is a Riemann fractional derivative. Find rho and ux satisfying condition, satisfying equation this, and using this following special condition. As the author proves, the problem has a unique solution if this inequality holds. We consider a slightly different approach to the inverse problem, and we obtain the following result. Consider the following Cauchy problem. Find the value of order rho and solution Ux of this problem with use the following additional condition. this problem we call this problem is forward problem. The forward problem has a unique solution, and this solution has the form. To find the parameter unknown parameter rho, we use this additional condition. For this, and additionally, we use the following lemma, which is monotonicity of symmetric Leffler function with parameter rho. Yeah, between 0 and 1, and lambda be positive, is positive. Then the function is decreased monotonically with respect to rho. The proof of lemma as follows. Let rho 1 and rho 2 between 0 and 1. And we consider this expression. Using simple calculation, we have this equality. Consider this ratio. Using this inequality and x between 0 and 1, we have q is less than 1 for all k. Therefore, this symmetric function is monotonically decreasing with respect to rho. Using this lemma, we give the following main result. Let x this 0 between 0 and 1, and lambda is positive. Since in this problem is a unique solution if and only if this inequality follows. Using additional condition and solution of for a problem, we have the following equality. Using lemma 7, we prove we obtain that unique solution of the inner problem. Additionally, if let rho 0 between 0 and 1 and x0 belongs to this interval, and lambda is negative, then the inner problem has a unique solution if and only if the following inequality falls. The proof of theorem follows from theorem 4. Theorem 4 is which is the monotonicity of this function with respect to rho. Thank you for your attention.
Thank you, Professor, for the nice presentation. Now it's time for questions. So you can unmute yourself and ask your question or write in the chat box. So, Professor, can you take us to slide 25? Slide 25. Yes. So consider the initial boundary value problem for the differential equation. So what are the values for the delta and rho?
This is delta sigma is one-dimensional fractional Laplace operator. This equation consider with Dirichlet boundary condition.
Okay. Then let's go to page 5. Okay, so page 5, on the definition of mod, we have rho is greater than 0. So rho being greater than 0, does it have a maximum value that rho can attain, or rho goes up to infinity?
Yes. There is rho is positive can we continue to infinity and mu and z belongs is arbitrary complex number. This row is positive. This row is positive arbitrary number.
Okay, okay. Thank you. So please, you are still, if you have a question, kindly unmute yourself and ask.
Sorry, may I ask a question, Professor? Ilyas Hijab, please show me the slide number 35. Yeah.
It is
Yeah. In the problem 17, you considered homogeneous equation, and my question is, can you obtain the similar result for the non-homogeneous case also for this problem?
Thank you for
Yeah.
your question. I don't see for non-homogeneous equation, but it's possible to find for non-homogeneous equation and find the value of order row and solution UX.
Okay, thank you. Yeah.
Okay. So I don't think there are more questions. So we can stop sharing, and we thank you for having our invitation, and we are looking forward to meet again in the future. Thank you.
Thank you. Professor.
Dear Professor Santosh Kumar, are you in the room with us?
Yeah. Yeah.
Could you
Yes,
please
sir.
try to share your screen? Good morning. Good afternoon.
Good afternoon. You are comfort.
Sorry?
Yeah. Mute. Yeah. Mute.
Sure.
Yeah. You are. It's all right.
Okay.
Okay, sir. Yeah.
Thank you. Good morning, good afternoon to everyone. Right now we're gonna have the presentation by Dr. Upadhyaya. Thank you very much for sharing with us this presentation. We're very pleased to have you today. He comes from the Department of Mathematical Science of the Indian Institute of Technology, Banaras Hindu University. And his presentation is titled Weinstein Pseudo-Differential Operators. The time is yours, Professor. Thank you very much.
Thanks. Thanks, professors. And title of my talk is the Weinstein pseudo-differential operators. These are the outlines, introductions. In introductions, standard notations, definitions, and the properties, the Weinstein transform. Second is the translation operator associated with the Weinstein transform. Third is the pseudo-differential operators involving the Weinstein transform. Fourth is an integral representation of the pseudo-differential operator involving the Weinstein transform and its various estimates. LP-LS, LP-alpha-S boundedness of pseudo-differential operators. How the pseudo-differential operators in heat equations. And the seventh is some recent works on pseudo-differential operators involving the Weinstein transforms. Eighth is the recent works, and the 9 is the conclusions, and 10th is the reference. Introductions is this is the simple idea about when the people open their eyes in the early morning, their sensory organs receive signals from the surrounding environments. These signals are processed by the brain and stored as information which may be finite or infinite in nature. The information carried by these signals is transmitted in form of waves, and the brain interprets them, allowing people to respond, for example, through speech. By generating this process of receiving, transforming, and interpreting informations, the concept of an integral transform arises. In many literatures, integral transform signifies the adequate informations of the time frequency localizations. This gives applications in many areas of mathematical sciences and engineering. The Fourier transform is an integral transform which is an representation of absolutely integrable functions and complex exponential type kernel. The Weinstein transform, which kernel acts the product of exponential functions and the normalized Bessel functions of the first kind with absolutely integrable function. Pseudo-differential operator and nice integral representations form a bridge between the integral transform and the partial differential operators. Aforesaid operators are called the generalizations of the partial differential operators. They play a significant role in the problems of partial differential equations, numerical analysis, and the quantum physics. Algebra and the calculus of pseudo-differential operators were developed by Hormander, Hahn, and Nirenberg in mid-1960. Hormander, Kato, Hahn, and Nirenberg, Nagase, Krebs, Wang, Gedman studied the problems of pseudo-differential operators by exploiting the theory of Fourier transform. The discrete pseudo-differential operators is an important tool in the mathematics and the computational science, and it allows researchers to analyze the approximate complex differential operators on discrete structure such as grids, lattices, or digital data. The importance of the discrete pseudo-differential operators lies in their ability to translate powerful continuous mathematical tools into discrete computational frameworks, enabling efficient analysis and simulations in science, engineering, and data processing. From few references, 16.2 and which are mentioned here, some standard notations, definitions, and the properties are given below, which are useful in other subsequent sections. R plus n, R to the power n plus 1. This is Rn cross 0 to infinity. This is like that way. N0 n plus 1. It acts like that way. X is equal to x dash xn plus 1. This is equal to x1, x2, xn, and xn plus 1 is an element of R plus n plus 1. And this the minus x, this is equal to, this is the in bracket minus x and x plus 1, and inner product as can be stated like that way. This is the summation of z equal to n plus 1, j equal to 1 to n xj yj. Norm of x square is written like that way. X to the power alpha. This is written x1 alpha 1, x2 alpha 2, xn alpha n, and xn plus 1 alpha n plus 1 var x belonging to R plus n to the power n plus 1 and alpha belonging to n0 to the power n plus 1. D alpha is the derivatives. This is defined like that way. And d nu I, this is written in partial derivatives form for mu belonging to n0 n plus 1 and and this absolute nu, this is written as nu 1 plus nu 1 plus 1 nu 1 plus 1 like that way. Factorial beta, this is equal to factorial beta 1, factorial beta 2 up to factorial beta n for beta belonging to n0 n plus 1. Gamma beta, this is gamma beta 1, gamma 2 beta 2, gamma n beta 1, gamma n plus 1. This is like that way. C0 R plus n to the power n plus 1, the infinite space of infinitely differential function on R plus to the power n plus 1. J alpha x J rho alpha x. Normally, C infinity R plus 1, the space of C infinite functions on R to the power n plus with compact support. Ck R plus R to the power n plus 1 plus the space of Ck functions on R plus to the power n plus 1. S star R plus to the power n plus 1, the space of C infinite R plus 1, the function of R plus to the power n plus 1. And S prime star R plus 1, the dual of Schwarzschild space. LP alpha R plus to the power n plus 1 denotes the space of Lebesgue measurable functions on R plus to the power n plus 1 such that norm of phi alpha LP alpha R to the power n plus 1, and this is the integral over R plus to the power n plus 1 mod of phi x to the power p d mu alpha x whole to the power p 1 by p less than infinity. 1 is less than or equal to p less than infinity, and norm of phi alpha LP alpha R to the power n plus 1 essential primum x R to x belonging to R to R plus to the power n plus 1 mod of phi x less than infinity, and where d mu alpha is equal to a alpha x to the power 2 n plus 1 n plus 1 dx. Dx is the Lebesgue measure on R plus to the power n plus 1, and a alpha is given by a alpha is equal to 1 by 2 pi to the power n by 2 to the power alpha gamma L plus alpha plus 1. Schwarzschild space by S star, we denote the set of all rapidly decreasing functions phi belonging to C star infinite R to the power n plus 1 such that mod of supremum x belonging to R plus to the power n plus 1 mod of 1 plus norm of x squared to the power k d beta x phi x less than infinity for k belonging to n0 and beta belonging to n0 to the power n plus 1. S star Rn plus 1 is called the Schwarzschild space, and it forms a vector space over the field of complex number. The topology on S star R to the power n plus is defined by the semi-norms Tk alpha Kl belonging to n cross n given by tau Kl phi supremum mod of beta less than or equal to n x to the power R plus to the power n plus 1 mod of 1 plus norm of x squared to the power k d beta x phi x. The Schwarzschild spaces star R plus 1 is subspace of LP alpha R to the power n plus 1 for all p belonging to closed interval 1 to infinity and alpha greater than minus half. Let p belonging to closed and open interval 1 to infinity and alpha greater than minus half, then Schwarzschild space S star R plus 1 is the dense in LP alpha R plus R to the power n plus 1. The Weinstein operator on R plus to the power n plus 1 for n plus 1 variables is defined by delta alpha nx. This is equal to summation of j is equal to 1 to n plus 1 dy square upon dy xj square plus 2 alpha plus 1 x n plus x to the power n plus 1 dy upon dy x plus 1. This is equal to delta n plus alpha n, alpha greater than minus half, where delta n equal to summation j equal to 1 to n dy square upon dy xj square is the Laplacian operator on Rn. of the first n variables, and L alpha, this is d by square 1 d by x square n plus 1 plus 2 alpha plus 1 by x to the power x n suffix n plus 1 d bar upon d by x n plus 1 is the Bessel operator on 0 to infinity for the last variable. For x belonging to c plus to the power n plus 1, the system d by square u upon d by x square x, this is equal to minus xi square ux. For 1 less than or equal to k less than or equal to n, L alpha ux, this is equal to minus xi square n plus 1 ux. For alpha greater than minus half, u0 is equal to 1, d by u upon d by x plus 1, 0 is equal to 0, d by u upon d by x, k 0, this is equal to minus I xi k. For k, for 1 less than or equal to k less than or equal to n, has a unique solution which is denoted by W alpha xi, and W alpha xi, this is equal to e to the power minus I x dash x dash xi dash xi dash and j alpha xi xn plus 1 xi n plus 1 for xi belonging to c plus to the power n plus 1, where x is equal to x dash xn plus 1 and xi is equal to xi dash xi n plus 1, where j alpha the normalized Bessel functions of the alpha. And this normalized Bessel functions index alpha is defined like that way: gamma n alpha plus 1 summation k is equal to 0 to infinity minus 1 by k to the by factorial k gamma alpha plus k plus 1 x by 2 to the power 2k. Properties of this kernel W alpha xi. For all xi belonging to c plus n plus 1 cross c plus to the power n plus 1, we have W alpha xi x is equal to W alpha xi, this is e to the power minus I x dash xi z j alpha cap x n plus 1 xi n plus 1. WL minus xi, W alpha x minus xi, this is equal to, and this is equal to e to the power I x dash xi di j cap alpha x n plus 1 xi n plus 1. W alpha 0 xi, this is equal to 1 for nu belonging to n0 to the power n plus 1 d derivatives with respect to xi u times W alpha xi, this is less than or equal to the norm of x to the power nu e to the power norm of x imaginary of norm of xi. For all xi belonging to r plus to the power n plus 1 cross r plus to the power n plus 1, mod of W alpha xi less than or equal to 1. The Weinstein transform, these are the various references of the Weinstein transform. The Weinstein transform of function phi belonging to L1 alpha r plus to the power n plus 1 is defined by Weinstein transform of phi with respect to xi. This is equal to integral over r plus to the power n plus 1 e to the power minus I x dash xi z j cap alpha x n plus 1 xi n plus 1 phi x mu alpha x for all xi belonging to r plus to the power n plus 1, where d mu alpha x is the measure on r plus to the power n plus 1 given by 1.3 equations. Let phi belonging to L alpha 1 r plus to the power n plus 1 such that Fourier transform, Weinstein transform of phi belonging to alpha 1 L alpha 1 to L1 alpha r plus to the power n plus 1. Then the inversion formula of the Weinstein transform is the phi x is written by 1.112. Properties of the Weinstein transform. Let phi belonging to L1 alpha r plus to the power n plus 1. Then the function Weinstein transform of phi is continuous on r plus to the power n plus 1 and norm of Weinstein transform of phi L infinity alpha r plus to the power n plus 1 less than or equal to norm of phi L1 alpha r plus to the power n plus 1. Let phi belonging to S plus R plus n plus 1 and k belonging to n0. Then Weinstein then Weinstein transform of the derivative delta k alpha nx phi xi, this is equal to minus 1 to the power k norm of psi to the power 2k f Weinstein transform of phi with respect to xi, and derivatives of delta to the power k depending on alpha n xi Weinstein transform of phi with respect to xi, this is equal to Weinstein transform minus 1 to the power k norm of x to the power 2k phi xi. The Weinstein transform, Weinstein transform is a topological isomorphism from S star r plus to the power n plus 1 onto itself, and my inverse Weinstein transform of phi, this is equal to Weinstein transform of phi minus xi for all xi belonging to r plus to the power n plus 1. If phi xi belonging to S star r plus to the power n plus 1, then we have integral of r plus to the power integral over r plus to the power n plus 1 phi x I x bar d mu alpha x, this is equal to integral of r plus to the power n plus 1 Weinstein transform of phi xi and Weinstein transform of psi xi bar d mu alpha xi. The Weinstein transform F alpha extends uniquely to an isometric isomorphism on L square alpha r plus to the power n plus 1. Now we have integral over norm of mod of phi x square d mu alpha x, this is equal to integral over r to the power n plus 1 mod of f alpha phi xi square d mu alpha. The continuous linear functionals on S star, S prime r plus to the power n plus 1 are called tempered distributions and are denoted by S dash star r plus to the power n plus 1. If F belonging to LP alpha r plus to the power n plus 1, the tempered distribution associated with F is defined by an inner product Fi. This is integral of r plus to the power n plus 1 fx phi x d mu alpha x phi belonging to S star r plus to the power n plus 1. The Weinstein transform of F belonging to S star dash r plus 1 is defined by an inner product F alpha F phi, this is equal to F and F alpha phi. For phi belonging to S star R plus to the power n plus 1. Theorem is the Weinstein transform is a topological isomorphism from S star S dash star R plus 1 unto itself, and in angular bracket you can thus write F Weinstein inverse Weinstein transform of F phi. This is F inverse Einstein transform phi for phi belonging to S star Rn plus 1. The translation operators associated with the Einstein transform. For all x, y, z belonging to R to the power n plus 1, the following formula holds: W alpha minus xt, W alpha yt, this is equal to integral over R plus to the power n plus 1, W alpha minus zt, d alpha xyz, d mu alpha z. If S star R plus to the power n plus 1, then the translation F associated with the Weinstein transform can be expressed as translation tau alpha x I y, this is equal to integral over R plus to the power n plus 1 phi z d alpha x y z d mu alpha z. Let phi psi is an element of L1 alpha R plus to the power n plus 1. Then from 13, the Weinstein convolution phi psi is given by phi convolution psi x. This is equal to integral of R n plus 1 tau alpha x phi y psi y d mu alpha y. This convolution is commutative associated and it satisfies the following properties. This theorem indicates that for all phi psi belonging to L1 alpha R plus 1, then phi convolution psi is an element of L1 alpha R plus 1, and we have Weinstein transform of phi convolution psi. This is equal to Weinstein transform of phi into Weinstein transform of psi. Let PQR is an element of closed interval of 1 to infinity, such that 1 by P plus 1 by Q minus 1 by R is equal to 1. Then for all phi belonging to LP alpha R plus to the power n plus 1 and psi belonging to LQ alpha R plus to the power n plus 1, then the function phi star phi belonging to LR R plus to the power n plus 1, then we estimate the following norm. Norm of phi convolution psi LR sigma R plus to the power n plus 1, this is less than or equal to norm of phi LP alpha and norm of psi LP LQ alpha R plus to the power n plus 1. Pseudo-differential operators involving the Weinstein transform. Let M belonging to R we find Sm to be the set of all functions sigma xi in C infinite R plus to the power n plus 1 cross R plus to the power n plus 1, such that for all k belonging to n0 and beta gamma belonging to n0 to the power n plus 1, there exists a constant C beta gamma greater than 0, depending only on beta and gamma, for which mod of derivatives v with respect to psi, derivative gamma times with respect to s, sigma xi, this is less than or equal to c beta gamma mod of 1 plus norm of psi square to the power m minus beta by 2 1 plus norm of x square minus k by 2. Let sigma xi be a symbol. Then phi belonging to s star r plus 2 to the power n plus 1, the pseudo differential operator T sigma associated with sigma is defined by T sigma phi x. This is equal to integral over r plus 2 to the power n plus 1 e to the power I x xi and j cap alpha x n plus 1 xi n plus 1 sigma xi Einstein transform of phi xi d mu alpha xi. In view of this, this 1.10 equations, the last expression can be written as T sigma phi x. This is equal to integral over r plus to the power n plus 1, r plus to the power n over w alpha x minus xi, sigma xi, Einstein transform of phi psi d mu alpha xi. Let Px delta alpha n x be a linear partial differential operator on r plus 1 such that Px d alpha nx, this is equal to gamma is equal to 0 to m by 2 c mu by s d gamma alpha nx, where all the coefficients c gamma x having bounded derivatives of all orders and delta alpha nx with the Einstein transform. Then the polynomial pxi in xi defined by pxi, this is equal to summation of gamma is equal to 0 m by 2 c gamma x into norm of psi square to the power gamma is in Sm m by 2 to the power n. Then by the theory of the Einstein transform, the following representation is obtained in form of pseudo differential operator Px delta L alpha n x phi x. This is equal to integral of r plus to the power n plus 1 e to the power I x dash I dash gamma j alpha x n plus 1 xi n plus 1 Px xi Einstein transform of phi xi d mu alpha xi for phi belonging to h star r n plus 1. This lemma 3.4, this represents that we prove the following relations for p belonging to n0 and x belonging to r plus to the power n plus 1. 1 plus norm of x square to the power p, this is equal to summation of p is equal to 0 to p depending on n1 n eta 1 eta n plus 1 summations greater than or equal to 0, PQ and Q n1 eta 1 and eta n plus 1 x to the power 2n, where eta is equal to eta 1 up to eta n and eta n plus 1 is an element of n0 to the power n plus 1 such that mod of eta less than q. Let alpha greater than minus half and xi is an element of r plus to the power n plus 1 plus r plus to the power n plus 1. Then we show that for gamma belonging to n0 to the power n plus 1, we have d gamma x e to the power I x1 xi1 plus I xn plus xn j cap alpha xn plus 1 xn plus 1 I gamma e alpha xi gamma e to the power I xi1 plus plus xn plus xn plus 1. Integral of minus 1 to 1 minus t square to the power alpha minus half t to the power gamma n plus 1 e to the power I x plus 1 xi n plus 1 dt, where e alpha gamma n plus 1 upon in under root gamma alpha plus half. Choose gamma n plus 1, eta n plus 1 is an element of n0 n. Then gamma n plus 1 is even, and gamma n plus 1 is a greater than 2 eta n plus 1, then we get x n plus 1 to eta n plus 1 integral over minus 1 to 1, 1 minus t square to the power alpha minus half t to the power gamma t to the power gamma n plus 1 t to the power I x n plus 1 xi n plus 1 t dt. This is equal to minus I 2 to the power eta n plus 1 divided 2 n plus 1 divided xi to the power n plus 1 integral of minus 1 to 1 minus t square alpha to the power alpha minus half t to the power gamma n plus 1 minus 2 eta to the power n plus 1 t to the power I x n plus 1 xi n plus 1 t dt, where the integral of the right hand side up to 3.7 is bounded by the beta function. This lemma indicates that the let alpha greater than minus half and gamma is an element of n0 to the power n plus 1. Then for phi s star belonging to r plus to the power n plus 1, xi gamma xi to the power gamma xi n plus 1 to the power 2 alpha plus 1 Einstein transform of phi xi is an element of s star r n plus s star r plus to the power n plus 1. This theorem, let sigma belonging to s to the power m and m belonging to r. M belonging to r be a symbol. Then the pseudo differential operators. Then the pseudo differential operator. Then the pseudo differential operator T sigma associated with sigma maps to the Schwarzschild space S star R n plus 1 into itself. The pseudo differential operator T sigma associated with symbol sigma maps the Schwarzschild space S star R to the power n plus 1 continuously into itself. More precisely, if phi s converges to 0 in S star R n plus 1, then T sigma phi s converges to 0 in S star R plus the power n plus 1 as s tending to infinity. And integral representations, the functions sigma xi associated with the symbol sigma xi and defined by sigma x. This is integral of w alpha eta xi and w alpha x minus eta sigma x eta d mu eta will play a fundamental role in our investigation. And estimate of sigma x is given by the following lemma. Let sigma belonging to s to the power m belonging to r, then the following inequality holds. Norm of sigma xi, this is less than or equal to em p 1 plus norm of psi squared to the power minus p 1 plus x squared to the power 4p minus k by 2, where E alpha mp is a positive constant and pk is an element of n0 such that m is less than minus 2 alpha minus n minus p minus 2. If sigma belonging to s to the power m belonging to r, then the pseudo differential operator associated with sigma can be represented in the following form. T sigma phi x, this is equal to integration over sigma x I phi I d mu alpha xi for phi belonging to x star to the power n r plus to the power n plus 1, where sigma xi is defined in 4.1, and involved estimate that is convergent for m less than 2 alpha minus n minus p minus 2 in lemma 4.1. Let sigma belonging to s to the power m and m belonging to r, then sigma xi, this is integration over r plus to the power n plus 1 w alpha eta xi w alpha x to the power minus n c sigma x m d mu alpha n can be expressed as integrations of r plus to the power n plus 1 w alpha eta minus xi sigma x xi d mu alpha. This is equal to w alpha x to the power minus 1 c sigma x eta. This is the theorems. Let u belonging to s star r plus to the power n plus 1, then the pseudo differential operator T sigma associated with symbol sigma belonging to s m belonging to r can be represented like that, where T sigma u x. This is equal to double integral r plus to the power n plus 1 e to the power I eta dash xi dash j cap alpha eta n plus 1 xi n plus 1 sigma x xi Einstein transform of u eta d mu eta and d mu alpha xi, where sigma is defined in 4.1 and all involved integrals are convergent. Then for kp belonging to n0, alpha belonging to n, such that p is greater than alpha plus n by 2 plus 1 and L is greater than alpha plus n by 2 plus 1. The translation operator associated with the Einstein transform. For all x, y, t belonging to r plus to the power n plus 1, then the following formula holds. W alpha minus xt, W alpha yt, this is the integral over r plus to the power n plus 1, W alpha minus zt, d alpha xyz d mu alpha z. Let phi belonging to s star r plus 1, then the translation of phi associated with Einstein transform can be expressed like that way. 4.7. Let phi psi belonging to L1 alpha r plus to the power n plus 1, then the Einstein convolutions of phi and psi is defined by integral r plus 1 translation operator of phi y psi by d mu alpha y. This convolution is commutative associated and it satisfies the following properties. This is this property like that. LB, these definitions. Let C belonging to S to the power m and m belonging to r. Then for each fixed x belonging to r plus to the power n plus 1, kxz is defined by integral of r plus to the power n plus 1, w alpha minus z eta sigma x eta d mu alpha eta for z belonging to r plus to the power n plus 1. This is the following estimates. Let sigma belonging to s to the power m, for m belonging to it, then the following inequalities hold. Mod of kxz, this is less than or equal to c alpha m p 1 plus norm of z squared to the power minus p into 1 plus norm of x squared to the power minus k by 2, where c alpha mp is a positive constant and kp s belonging to n0 such that m is less than minus 2 alpha minus n minus s11. Let s belonging to r denote LP alpha s r plus 1 less than or equal to p less than or equal to infinity by the space of all function phi belonging to s star prime r plus 1 which satisfies norm of phi LP alpha S R plus to the power n plus 1. This is equal to norm of 1 plus xi square to the power n by 2 phi xi LP alpha R plus to the power n plus 1, where 5.4 equation holds that norms. Let alpha greater than minus half p dash q dash r is an element of closed interval of 1 to infinity such that 1 by p dash plus 1 by q dash minus 1 by is equal to 1. Then for u belonging to S prime r plus to the power n plus 1, the pseudo-differential operator T sigma associated with symbol sigma belonging to S m belonging to R maps continuously L alpha p dash r plus 1 to L alpha k r dash r plus n plus 1. Moreover, norma p sigma u L r dash alpha k r plus to the power n plus 1 less than or equal to C alpha k m p norma of 1 plus z squared to the power of p L q dash r plus 1 and norma q LP alpha r plus to the power n plus 1, where C alpha k m p is the positive constant or p belonging to n and q dash is greater than 2 alpha plus n plus 2 to the power p. These are the various applications of the pseudo-differential operators of the heat equations. The pseudo-differential operator UX, this is the inverse of these functions, and this is defined like that way. 6.2. You see the solutions of this solutions is the pseudo-differential operator. This is the integral over r plus to the power n plus 1 e to the power I x dash xi dash j cap alpha xn plus 1 xi n plus 1 sigma t xi Weinstein transform over xi dv xi. Some recent work exploiting the theory of Weinstein transform. Many observations are found which are given below. Sartaj and Upadhyay discussed the boundedness and the compactness results of the for the symmetric global pseudo-differential operators of LP alpha r plus 1 type Pavlov space H L R RSP alpha using symmetric global symbol global symbol sigma xi in M1 M2 for M1 M2 belonging to R. Properties of the minimal maximum pseudo-differential operators are discussed and weak solutions of the symmetric global. Yes. Sartaj and Upadhyay also investigated LP alpha R plus to the power n plus 1 boundedness of pseudo-differential operator associated with certain class of symbol S0 and its many auxiliary results are found. And the journal is the Philomate, which is published in 2023. And the same authors investigated about the boundedness of pseudo-differential operator with homogeneous symbol classes and discussed about the commutator between two pseudo-differential operator on HR alpha 2. Pseudo-differential operators of homogeneous symbol associated with Weinstein transform, Acta Mathematica, Sinica, English series. Srivastava, Yadav, and Upadhyay investigated certain family of pseudo-differential operator associated with symbol class SR omega on spaces omega R plus to the power n plus 1 for the real value convex function omega. Various properties of the pseudo-differential operator AFG associated with class SRLM and the pseudo-differential operator AFG associated with the indicative symmetry and the L2 norm of the fluid differential operator AXD with the indicated MT and omega T are discussed. Class of fluid differential operators involving the Einstein transform. Mathematical methods in applied sciences 2025. Ansuya Yadav and Padhyay investigated the solvent set and essential spectrum of the fluid differential operator. They established connections between LP multiplier and the spectral theory. This paper was published in the Journal of Fluid Differential Operators in 2025. And the same and Sitaram Yadav and Padhyay discussed the banana space by looked up the test functions, running time, ultra distribution. H omega A is defined by taking the weight function omega, and this paper is published in Philomet 2025. Sartaj, Priyanka, Balwant, and Padhyay introduced the fluid differential operator on Z plus to the power n plus 1 and the boundedness results on Frederick operators on L2, L2 alpha T to T plus N plus 1 types of Bloch space X S2 alpha Z n plus 1 involving the Fourier Bessel transform, fluid differential operators, and involving the Fourier Bessel. This is the Mediterranean Journal of Mathematics 2025. And some other works, Sartaj, Priyanka, Balwant, and Padhyay explored the LP and ZL plus boundedness and compacted of symmetric global fluid differential operator for 1 less than or equal to 3 less than infinity its various properties, mapping properties of the fluid differential operator on discrete Sobolev space H and SP alpha by considering the theory of discrete Fourier Bessel transform. It means the Einstein transform and is the Journal of Fluid Differential Operators and Applications 2026. Many intuitional idea of the integral transforms and its fluid differential properties and are exposed. Continuity property of the fluid differential operator T sigma on Schwarz spaces R plus to the power n plus 1, which are useful for further extensions of the set theory are shown. The integral representations and the concept of the convolution regarding the Einstein transform are given using the above concepts. Various estimates of the integral representations and the LP alpha S R plus 2 power n plus 1 type spaces and associated results are discussed. The solutions of the heat equations is given and it is expressed in form of fluid differential operation by using the Einstein transform. These are the various references. This is the references. This is the references. This is the references. Thank you.
Thank you very much, Professor. It was a great presentation. Thank you very much for submitting your work with us. Now the space is open for questions. Please feel free to write them in the chat or raise your hand. Let's see. Well, while the attendees think about their questions, I would like to know if you and your colleagues have thought about investigating other Hormander classes. I understood that you are considering SM10. Are there any ideas if the other classes with different parameters can be considered?
Yes, I could not consider the Hormander classes. I just consider the concept of the most probably Jedman and Wang.
Okay. Thank you very much, Professor. Any other questions? Okay. If there are not any other questions, thank you very much, Professor, again for joining our conference. Okay,
Thanks.
there is a question in the chat. They are asking if there are applications of this technique in other transforms.
Just in the presentations we have given this techniques, we can use the heat equations. And we use this technique LP bounded net and Sobolev type species.
Okay, great. Thank you, Professor. Thank you again for joining this conference. It was a pleasure to have you here. And for the rest of the attendees, we're gonna take the break until 18 Central European Time with the presentation by Professor Jorge Marquez. Thank you very much. Until then.
Thanks, professors.
I saw between the participants Nicolás Walteros and Natalia Gudelo, who actually join us in our activities. Very nice to have their participation. So, quizás si Nicolás y Natalia quieren saludarnos, está bien, estamos en break. Como Manuel nos comentó, tenemos una hora de break.
Hi.
Hola, hola.
Hola,
¿Cómo estás,
¿cómo es?
Nicolás?
Saludos a toda la comunidad de IGNAM. Aquí desde el transporte público. Ahorita voy para clase.
Ah, muy bien, mira.
Están muy interesantes las charlas. Que puede estar en dos, muy poquitas, pero pues ha sido más por cuestión de tiempo.
Claro. Muchas gracias por conectarte en medio de tu agenda. En medio de tu agenda. Muchas gracias.
Bueno, y saludos por ahí a Edison también. Por
Sí,
ahí lo he visto conectado con la movida de IGNAM.
sí, Edison se ha unido recientemente a ayudarnos con la organización.
Un abrazo gigante, mi querido Juan, mi querido Nicolai.
Un
Excelente.
abrazo a todos.
Natalia también nos acompañó ayer, ¿verdad? Nos ha estado acompañando. Si quieres hablar, Natalia, está bien para saludarnos.
Sí, desde antier he estado conectada a algunas de las charlas.
Muy bien, excelente. Excelente. ¿Desde qué parte nos sigues, Natalia?
De la Universidad del Valle, en Cali.
Ah, ok, ok. Excelente, excelente. Hace mucho tiempo estudié en la Universidad del Valle. Hace mucho.
Sí, eso lo sé con el profe Julio.
Oh, muy bien, excelente. Gracias por unirte. So thank you very much to all the participants. We just were interacting with our friends from ICMAM, actually several researchers from Colombia.
Good evening to everyone. Good evening, Professor Marquez.
Oh, good evening. Good evening. Good afternoon here. Do you hear me?
Yeah, I can hear you well, Professor. Thank you.
Thank you. Nice to meet you.
Nice to meet you as well. It's a pleasure to have you here. Could you please try to share your screen, Professor?
Okay, let's try. Sorry, I will exit. Then I come back. Okay, sorry.
Okay, no problem.
I have
We'll
some
wait for
problem.
you.
Okay, with the document. Okay.
No problem. Thank you. Dear Professor Marquez, can you hear me? Dear Professor Marquez, can you hear me?
I have permission to share the. Okay.
Yes. Yes,
Okay.
please.
Now I think I found it. Okay.
Okay.
Sorry. Uh,
Okay. We can see your screen, Professor.
one moment, please.
Okay.
I'll put in. Okay, in the full mode screen. Okay.
There we go. Thank you very much, Professor. Okay. Welcome everyone from the break. We are glad to have you back here in session. Thank you to Professor Jorge Marquez from University of Coimbra, Portugal, for joining us with these presentations. Thank you very much for collaborating with us. We are very pleased to present his talk titled Global Existence of Small Data Sobolev Solutions to Hyperbolic Models Generalizing Semi-Linear de Sitter Models. Thank you very much, Professor. The time is yours.
Okay, thank you. I'd like to thank to organizers for the opportunity to share our work. My talk is based on joint work with Professor Michael Reisig. I divide my presentation in 6 points: introduction, methodology and results for two kinds of models, then conclusions. I start with some background and motivation. For semi-linear models with the family of power nonlinearity on the right-hand side, models of phi power to power p, we are asking for the critical exponent, which divides the range p greater than 1 into subsets. In the supercritical, p greater than p critical, you can prove the global in time well posedness of small data Sobolev solutions. In the subcritical case, p lower than p critical, you can prove blow-ups results regardless of smallness of the initial data. Often, the main goal is to find the critical exponent, a threshold between blow-up phenomena and existence in time of small data results. Here we have the semi-linear de Sitter model. This is the Cauchy problem. On the right-hand side, we have the power P of models of phi. Here you have the speed of propagation, exponential of minus 2 times. N is the space dimension, in this m square is the coefficient of the mass, and F and G are the initial data. In the result 1 from in 2025, the authors was classified a generalization of the model with the space dimension n replacing by a any positive constant. It was proved the following. If m greater than half of b, then it was proved global in time well possessedness of Sobolev solutions belongs to the space of continuous functions from this time interval to h gamma. With gamma between two values. For small data, f belongs to h gamma plus 1/2, with gamma between 0 and 1/2. G belongs to L2. This range is not empty if and only if P is greater than n over B. That is, P increases as B tends to 0, if P greater 1 for B bigger or equal n. So we cannot expect it, a critical exponent. Now we introduce the following model. This is the Cauchy problem for the semilinear hyperbolic equation. We assume that the m1 and m2 are positive constants. The speed of propagation A is positive, decreasing and integrable, so over time interval. And the capital A is equal to integral from t to infinite of AS. You have the term of dissipation. Now you have the Laplacian, and here the term of the mass term. Our model is a generalization of the C-term model. In fact, if AT is equal to exponential of minus t, then this ratio A over capital A, this is equal to 1 for all t. It seems to be a challenge to study the above model because the interplay between the two constants, m1 and m2, has a strong influence on expected results. We propose a classification of models in mass dominant or dissipation dominant. To explain, in order to explain it, we introduce an assumption on the propagation speed, and we do a change of dependent variable. Let's see, the assumption A0 is the following. We have this ratio between two limits, and you have d1 and d2 are constants. Then we do the change of variable. The previous variable is equal to this product, an exponential with exponent r some constant, some negative constant r times this integral times the new dependent variable. So first, if you choose r equal minus half of mu, then the dissipation term disappears, and I get a new mass term. On the left-hand side of the equation, on the right-hand side of the equation, we have a new term, an exponential, with the negative exponent, which multiply by the power of the new variable u. This mass term satisfied the following inequality. Using the assumption is zero, the mass term satisfies this inequality. If this coefficient is positive, then we have a lower bound to the mass term. Makes sense the following definition. If this coefficient is positive, then the model is called mass dominant. On the other end, you can choose the larger root of this quadratic equation. If you do so, then you have a new equation with a new coefficient for dissipation. Mu1 is equal to times R0 plus mu1 is a positive, and the mass term it is bounded. We can observe then when we replace R by R0, this term is zero. So the mass term is positive and bounded above. This choice of R0 guarantees that the mass term is at least non-negative, and hence you have this definition. If this coefficient is negative, the model is called dissipation dominant. Taking into account then 2R0 plus M1 is equal to this expression, we propose a subclassification of dissipation dominant models. If 2R0 plus M1 minus U1 negative, then the dissipation dominant model has a non-effective dissipation term. But if 2R0 plus M1 minus D2 greater than zero, then the dissipation dominant model has a non-effective dissipation term. For example, in the Sitter model, the speed of propagation, this equals exponent minus t, alpha is equal to 1. And we have the following classification. If M2 greater than half of M1, then it is a mass dominant model. And if M2 lower than half of M1, then it is a dissipation model. When in the equality, we call it a balanced dissipation and mass model. In addition, if M1 greater this value, then the Sitter model has a non-effective dissipation. But if M2 less than the value, this value, then the Sitter model has a non-effective dissipation curve. In this case, this is the value of R0, which depends of the coefficients M1 and M2. Sorry. Now, Now we consider the model 1, which is a mass dominant model. And we need to introduce more regularity on the speed of propagation. So the assumption A1, this is assumption to the models of the derivatives of A. First, second, and the third derivatives, which are controlled by these expressions. Here you have constants, ck. It is related with the order of the derivative. From A1 and A2, it follows the following condition. I need that for estimates. We point out then the expression of mu includes a prime, so that to evaluate the first two derivatives of mu, we will need three derivatives of A. An efficient tool for studying nonlinear equations is to construct the fundamental solution of the associated linear equation. We have the linear equation because the right-hand side is 0. Since this equation is has time-dependent coefficients, I shall to solve the family of a parameter dependent linear Cauchy problems. With the initial time as a parameter s, greater or equal to 0. So we applied the partial Fourier transform with respect to x, and you reduce the previous equation to a parameter dependent ODE, with V is Fourier transform of mu. We have the equation and the initial data. Capital D of t, this is the Fourier derivative on time. And you have here an expression represented by Japanese brackets. This symbol is given by the square of the sum of these two terms. Now I can't solve directly this equation. Instead of theory of special functions, we are able to use the tools of the WKKB analysis. We consider the extended phase space. It is a hyperbolic region. We split this region into three zones. The exterior zone, this is for higher frequencies. The interior zone, this is for lower frequencies, and there is a middle zone between the previous two. The zones depends of two parameters. N is sufficiently large and epsilon sufficiently small. There are two separate lines, T epsilon 1, which satisfy that equation. Between the exterior zone and the middle zone. The other separating line, T epsilon 2, divide the middle and the interior zones. the constant n is chosen later. Then we will derive energy estimates in every zone. The second order ODE can be written as a first order system. We consider no, this is the first order system. We have the Japanese brackets here, the derivative over the brackets. Then we applied the first step of the diagonalization procedure. It requires C2 regularity of the speed of propagation. Then we diagonalize the matrix and arrive to the first order system. This system here D0 is a diagonal matrix, and R0 this is one. This is another one. This is the R0. First, we estimate in the fundamental solution in the middle zone, applying one step of diagonalization. We can integrate the norm of R0, the remainder R0, this value. The fundamental solution in the middle zone satisfy this equation, and it is uniformly bounded. Then we estimate the fundamental solution in the exterior zone. We have the Japanese bracket is equivalent to this product, speed times the models of Xi in this exterior zone. Here we carry out the second step of the diagonalization, keeping the structure of the main diagonal part. This is very technical, but is standard in standard. We prove that the new remainder R1 is integral, which is given by a product to the two matrices, the inverse of N1 times B. There is formulas for B. Here F1 F1 is a diagonal matrix. These N1 have zeros on the principal diagonal, and F1 minus R0 is the commutator relation between the matrix D0 and N1. So we can conclude that the fundamental solution is represented by a product of some matrix, and it is uniformly bounded. We note that this matrix is diagonal, invertible, and Q1 can be represented by means of the Peano-Backus series. Finally, we estimate the fundamental solution in the interior zone, and we have some relations. Then will be two situations in this zone, which depends that inequality. H0 and C1 are constants. We have here in this slide H0 and C0. So if the condition is satisfied, then we can carry out the second step of diagonalization. Then we can estimate the norm of this matrix N1, which implies that then it is invertible, and the inverse satisfy the norm, the inverse satisfy this constant, this positive constant. On the otherwise, we stop after the first step of diagonalization, and we will integrate the norm, the integral of the norm of R0, and we get that. So we have to glue the estimates in the three zones, and we arrive at two statements. Two propositions, proposition 2.1, when this condition is satisfied, and the proposition in the following proposition 2 for the other case. Here we have the energy estimates for the solution, for the derivatives of solution, for the sum. Portanto, for this, a similar result in the case 2, when this condition this condition doesn't hold. We have the estimates, the energy estimates. Portanto, the solution and the derivatives are controlled. So, what can I do about this condition? We can say the following. It appears on the estimates of the fundamental solution. We show it is a possible second step of diagonalization as an improving influence. If you carry out the two steps of diagonalization, taking into consideration that constants, which depend of properties of A and some its derivatives, this coefficient becomes positive and small if M2, coefficient of the mass term, is large. So to every small and positive kappa, there exists a coefficient which depends the kappa, such that the condition for all M2 large, for M2 large. If you carry out only one step of the diagonalization, then we have no essential influence of coefficient M2 on this constant. The previous proposition allow to obtain final estimates in the physical spaces. We have the solution of the linear equation. This is a sum of two terms, K0 convolution with the first datum, K1 convolution with respect to x with the second initial datum. And this solution satisfies the following a priori estimates for all t. The norm, it's not the norm in the homogeneous overlap space H gamma is given lower or less or equal than a constant times this expression. You have an exponent, a negative a negative power of mu. Here, this is an exponential, and you have the sum of the two datas. The first data belongs to H gamma plus 1/2. The second data belongs to L2. So then we go to the semi-linear Cauchy problem. And I use the Duhamel's principle to the Cauchy problem. We may interpret weak solutions as solutions of the nonlinear integral equation. There is a sum, the two terms, linear solution, with this integral. Here we have an exponential with a negative exponent, and here the convolution with the power p of the modulus of the u in Sx. So we can get a corollary. If u1 belongs to L2, we have the following estimaton. I need this estimaton later. The estimate 21. In order to prove global existence of small data sublab solutions, we follow the standard approach. We consider an operator P given by a sum. Gu is the nonlinear term. We define a family of solution spaces. It is a family of weighted solution spaces. Solutions belong to these spaces and as finite norm. The norm is given by the supremo of the three factors. The norm u view in H gamma and these two powers. To estimate the nonlinear term, the fractional Gallardo-Nirenberg inequality comes into play. Then you can estimate this norm, the p norm, the absolute value of u in L2 is given by this, where theta is equal this expression if and only if p is between 1 and n over n minus 2 times gamma. So we estimated the nonlinear term, the norm in the homogeneous space, the norm, the difference into GU and GV. Then we have the following. We have to. It is enough to show two essential inequalities, 26 and 27. Once we prove that, we can assure that that P is a contraction map on this space y gamma of t. Then we apply Banach's fixed point theorem. And we can prove the unique fixed point in this space. It means that there is a global solution. Here, to conclude global in time existence result, we have to guarantee this integral condition. But this integral should be bounded by a constant. So here, this is the main result. And space dimension, and the space dimension gamma, the exponent of the Solar space, the space between 0 and 1p. P belongs this interval, and in addition to assumptions A1 and A2, we suppose this integral condition is bounded. Then we can conclude there exists uniquely global in terms of lab solution in this space to the Cauchy problem. Moreover, the solution satisfy the decay estimate. We have three factors: a negative power of mu, a negative power of capital A, and an exponential with the negative exponent. Here we have the sum of the norms of the initial data. We have an example for the sitter model. We have an example. We can estimate the integral condition, and we can conclude the following: if m1 greater to c, then the integral condition will provide that p greater this value. So we point out the following range for p. Could be not empty. It means that we can find m1 coefficient of dissipation term such that this range is satisfied for the following inequalities. So we have a remark about the improving influence of the mass term on the range of P. The constant h0 depends only on the properties of the speed of propagation. So m2 is large enough. If m2 is large enough, then the integral condition is satisfied. And we can conclude we have global in time well positives for small data sublab solutions for P in this interval. So we cannot expect in this example a critical exponent larger than 1. This result corresponds to a result of the paper of the Michael Reisig, paper the 2025. Now, from now, I do considerations on the model 2, which is a dissipation dominant model with no effective dissipation. We follow a similar approach. So now in this model we have one more term, with the dissipation, the coefficient mu1. This is a positive coefficient. The ratio A over capital A. R0 as you've seen, is the large root of this quadratic equation, and there is an upper bound for the mass term. So we similar to the model 1, we apply the partial Fourier transform with respect to x. Then you have a Cauchy problem for ODE with a parameter xi. this term in model 2, comparing with model 1. Here we have one more term. Now we have the assumption A4, the upper bound for mass term. The assumption A is the same, and then 2 is the same. Okay. Now in this model, we split the extended phase space only into zones. Hyperbolic zone for higher frequencies and a dissipative zone for lower frequencies. There is only one separating line. So we will derive estimates of fundamental solution in the both zones. I start with the hyperbolic zone. The second order ODE can be written as a first order system. We have this component with this one. We start applying the first step of diagonalization procedure. We arrive at the first order system. Again, D0 is a diagonal matrix. R0 is the following, depend of the mu1, the coefficient of the dissipation. We carry out the second step of the diagonalization procedure, and we conclude the following. The fundamental solution is represented by a product of matrices, and we have the norm of the fundamental solution in the hyperbolic zone is controlled by this square root, these expressions uniformly. Okay, now we have here the energy estimate. Again, we have this result. We have the models of the derivative, the solution, the model of solution times the model of the parameter psi. Now we estimate the fundamental solution in the dissipation zone. We define the microenergy, this vector. Then we have this system, and we consider Ejk, the entries of the matrix. So E1k, E2k, this is the column k of the matrix, the fundamental solution in the dissipation zone. Applying the Cauchy formula for linear ODEs, we get the following system of integral equations. We have here E2k and here 2. For convenience, for simplicity, we use another notation, capital E, given by that. Then we plug in the first expression in the second, and we get these two expressions. Using the assumption A4, the definition of the zone, we can bound the square root of the Japanese brackets by a constant times square of this ratio. So next we have to estimate we have to estimate this integral, two integrals, this one and the another one. For that, we establish a new assumption. Mu1 coefficient of dissipation greater than the maximum between D2 minus 1 is 0. And we get this lemma. We can observe this integral is less or equal to this expression. So the exponent of the capital A increase one unity, and the exponent of speed of propagation decrease one unity. The same in the another one. So we get a proposition with the estimative, the fundamental solution in the dissipative zone. Okay. If you glue the estimates on the two zones, we have to distinguish two cases. Case one, with this constant C is greater or equal 1/2. And we have energy estimates when this constant is satisfy this condition. And the second case, when the constant C is less than 1/2. So we follow the same procedure. Then in the model one, we have a proposition for the norm of the first component of the linear solution, the norm homogeneous Sobolev space H gamma. So you can estimate the norm of the linear problem, and you get this result. Okay. Then we move to the semilinear hyperbolic equation. And again, we use Duhamel's principle. And we have the main result for the second model. The second model, again, we have integral condition. It is necessary to satisfy this, to hold this integral condition for getting the global solution. We have to this condition. It should be held. Again, we have solution, and you have a decay estimate for the norm of the solution. We have the example for the sitter model. This is similar to the first one. We have the conditions. Okay. So we can conclude the following. I think I don't have much more time, but I can say the results we obtain. It is in correspondence with the blow-up result of this paper, the Tsutaya and the Wakasuki. Again, we have a loss of the critical exponent because of that. I finish with some remarks. Our results showed the improving influence of the mass term in comparison with damping term in mass dominant models. For some classes of models, we showed that there is a loss of critical exponent. It means that for all exponents, we have global in time existence of small data sublab solutions. Those results show that the question for critical exponent has to be modified to the question of critical nonlinearity. Finally, it could be a nice problem to study blow-up for this kind of the Cauchy problem, where the mass term is zero. We have only the term of the dissipation. As far as you know, there is only a result about blow-up. This is the result is in this paper of the Tsutaya and Bakasuki, 2022. Okay, and final, I have some references. Okay, thank you.
Thank you very much, Professor Jorge Marquez. Thank you for this very interesting presentation. I would like to ask the attendees if they have any questions. Please feel free to ask them by the chat, or you can raise your hand to ask the question. Okay, while the attendees think about their question, I would like to know um if there is any ideas, or do you have any directions on how to attack this problem when the solutions are not particularly small, or it does not have sense to ask that question?
Sorry, when the solutions are not
Particularly small, not necessarily small, or
okay. I think in this case, it is more difficult to obtain global existence, because in general there are blow up for these kind of problems.
okay, I see, I understand. Thank you, Professor Marquez. Are there any other questions in the public? I think everything is pretty clear. So thank you very much, Professor Marquez, for your presentation. We're very glad to have you here.
Okay, thank you.
Have a nice day.
Okay, thank you.
Now let me see. Okay, Professor Karin Teres-Howell, are you in the room? I think you are.
Hi, yes, I am.
Thank you very much. We're glad to have you here. Perhaps could you try to share your screen to check if everything is working?
Sure, thank you. Can you confirm that you can see me on the camera?
Yeah, we can see you and we can hear you well. Thank you
Great.
very much.
Awesome. Thank you. I'm going to try and share. Can you see that?
Yes, we can see your screen. Thank you.
Let me see if I can. I don't know if I can get it any better. Is it clear enough? Can you see it
We can
clearly?
read it. We can read it.
Okay. Okay, thank you. Do you want
Thank
me
you.
to wait to start?
We'll wait a couple more minutes, I think. Thank you very much. We'll let you know. Thank you.
Thank you.
Okay. Professor Karin Dresshol. Nice to meet you. Nice to meet you.
Hi.
Right. Nice to meet you. Thank you very much for accepting our invitation for this conference, accepting the invitation of Karina Navarro, actually the president of ICMAM Latin America. So then maybe we can start. Just let me introduce yourself. Let me introduce you a little bit. So it's my great pleasure to introduce our next speaker, Professor Karin Deres-Howell from the African Institute of Mathematical Science in South Africa, where actually she is the current executive director, right? So Professor Deres-Howell will talk about life just outside linearity an introduction to near vector spaces. So thank you very much.
Great, thank you. Can you confirm that you can hear me clearly?
Yes, we
Okay,
can hear you
great,
well.
thank you. All right, so I want to start by saying good evening to everyone, but also just to thank the organizers for this wonderful invitation to spend this time talking to you about my research. So thank you for that. I'm very excited to share the mathematics that I'm passionate about with you today. It's actually evening here, so this evening. All right, so the structures that I've been studying in my research area are called near vector spaces. And in this talk, I'm going to introduce you just to the most basic notions and give you a taste of why I think they're important, why I think they're interesting, and also just give you some insights into the work that I've been doing for the last years. And predominantly that has been looking at how these structures behave when you take them into other branches of mathematics outside of algebra. So what do I mean by that? For example, talking to experts in incidence geometry, if you look at some places where vector spaces are used, what would happen if you revisited those topics and replaced every vector space by a near vector space? What sort of properties would you see? What sort of behavior? And that's sort of how I've been working the last few years, just collaborating with experts in different branches and seeing what interesting things we can discover. And it's been a very fruitful exploration, and I'm very grateful to many collaborators who've walked this path with me. So just by introduction, I'm Karin Therese Howell. I'm based in South Africa. I'm affiliated to Stellenbosch University through my research. I have the rank of associate professor there, and I'm also since recently appointed as the executive director of AIM South Africa. I hope you don't mind, but in the last slide, I would like to share a little bit about AIM South Africa and also invite all of you to come and spend time or see how you can contribute. It's a very special place, and I'll tell you about that at the end. All right, so my talk will have three main parts. I'll give a short introduction, just explain to you what these structures are. Then I'm going to focus on a very simple construction for this evening's talk, just looking at constructing over ZP, because I find they're very accessible and they really get the message across of what the properties are that these structures have. And then I'm going to show you a very simple application of them, just illustrating a finite linear game and what effect swapping out a vector space with a near vector space has in that setting. And then hopefully I can convince you that these structures are as special as I think they are. And I think that they have many undiscovered applications. And that's sort of the purpose of the talk, to convince you of their interest, but also potential applications, perhaps in the area that you're interested in. There are a few authors who've looked at this notion of defining what a near vector space is. So maybe just taking a step back, in algebra, when we speak of a near structure, there's a number of structures that like this that already exist. For example, we have the structure of a near ring, which is a ring where one of the distributive laws is not necessarily required. So you weaken one of the distribute laws, and there's a whole field that has studied these structures called near rings, and they've been very useful and interesting. And in the same way, Andre was one of the authors. He's not the only one, but his work has been the predominant focus of my work. What he did was ask exactly the same for a vector space. So if we have a vector space, and in general, we don't require that one of the distributive laws hold, what do we get? And that is the structure that he called a near vector space. So we're going to see what this nearness means. Now, the definition, when you write it down, is quite a mouthful, and it, working through it is quite complicated, and understanding all the machinery behind it. But I'm just going to highlight what's important and then draw you to how we are going to construct, and that's all we need to focus on. So as with vector spaces, you start with a group. And you may wonder immediately, does it need to be abelian? Well, it will sort itself out as being abelian once we get to the second axiom. But you start off with an additive group and a set of its endomorphisms. And you ensure that in that set of endomorphisms, you have the zero map, the identity, and the inverse map. And then you ensure that the automorphisms are picked in such a way that the non-zero elements of A form a subgroup of the automorphism group of V, which we know is a group under composition. You need to ensure that A acts fixed point free on elements of V, which is exactly the property that we have for vector spaces as well. So what that means is if alpha x is equal to beta x, then x must be 0, alpha must be beta. And that's the predominant property in vector spaces that allows us to solve vector equations. The last property, if you think about what we know about vector spaces, seems rather strange. It's not something that we're used to, whereas I think the other ones are very much in line of what you would expect for a vector space. This is the added property that sort of sets near vector spaces apart from vector spaces, and I'll explain why. We have a structure called a quasi-kernel, which is a subset of V, with a property that that quasi-kernel can generate V as a group, which means you can take any element of V and you can write it as a sum of the elements from the quasi-kernel. And the quasi-kernel collects all the elements that have this linear property, which is that all the elements that belong to the quasi-kernel have the property that if I pick any two scalars, alpha and beta, I can find a gamma. It turns out to be unique, but such that I can write alpha x plus beta x equal to gamma x. And this property captures a certain linearity. And these elements are all grouped together, all the elements that have this property, and they are called the quasi-kernel. And our requirement is for this structure to be a near vector space, you need that set to be able to generate V additively. Already, if you're wondering about vector spaces, all elements of a vector space have this property. So for vector spaces, the quasi-kernel would be the whole space. It's also usually evident when you define a near structure, you define it in such a way that the structure that you derived it from, for example, a ring and a near ring, it always turns out that a ring is an example. A near ring is a ring is an example of a near ring. The structure would be an example of the generalization. And in this, these axioms too, if we were to check them, every vector space would satisfy them. So every vector space is a near vector space. And in that case, the quasi-kernel would be the whole space, since all the elements have this last property that they belong to QV. And QV, of course, would generate the entire V, since we know that there's a set, the basis that exists. Okay, so V is called our near vector space, or sometimes when we want to be clear on what our set of scalars is, we say V is a near vector space over A to just distinguish that. Just as with vector space theory, we speak about vectors and scalars, and we speak of scalar multiplication, the action of A on V. The fact that we require the inverse identity map to be in A ensures that V is an abelian group, which is a nice thing to know, and it also mimics what we know for vector spaces. And then you'll be relieved that, as with vector spaces, we have dimension that can be defined. It's again the notion of a basis, but with the added restriction that that set should sit inside the quasi-kernel. So the dimension would be uniquely determined by the cardinality of a generating set. And here it's exactly what we mean for vector spaces, meaning you can write every element as a linear combination of that set that you've proposed. And we do call it a basis, as we do with vector spaces. The only requirement is that those elements sit inside the quasi-kernel. So I always think of the quasi-kernel as a structure that preserves the linearity that still is retained in these structures called near vector spaces. And as I remarked, every vector space, if you spend a moment just looking at those axioms, turns out to be a near vector space with the property that the quasi-kernel is the whole space, which makes sense since we have both distributive laws holding. So Van der Walt was a mathematician based at Stellenbosch University many years ago, and he proved this result. And I'm not going to read it, but I'll just explain to you what it allows us to do. We refer to it as Van der Walt's theorem. Basically, it gives us the machinery to construct a near vector space from some near fields that you choose. Now, what are near fields? Near fields are the generalization of fields. So it's again got the axioms of a field minus one of the distributive laws. We don't need to go into all the details of that, but every field is a near field and ZP is a field. And so ZP will work as the near field in this construction that we're going to do. So without reading through the theorem, because it is a mouthful, what I'm going to explain to you is how we're going to use the theorem in a very accessible way to construct what for, I guess, most of you would be your first exploration and example of a near vector space. So basically, we start off with ZP. We know it's a near field, so we can apply the theorem. We take n copies. You can take as many as you want. So in our case, we're going to take 2. And in order to know how you may define the scalar multiplication to ensure that the axioms of a near vector space are satisfied, Van der Waals says you need to find multiplicative automorphisms of ZP and define the scalar multiplication in terms of those automorphisms. So we take, in our case, we're going to take 2 copies of Z5, and we're going to find the multiplicative automorphisms of Z5. We're going to pick 2, and what's going to happen is when we multiply by the scalar alpha to some n tuple, what we're going to do is instead of just multiplying by alpha, we're first going to apply this multiplicative automorphism to alpha, and the result will be multiplied by xi. So it's not the normal multiplication where we just multiply alpha in. We're first going to let the automorphism act on that scalar and then multiply the scalar in. So before we can do that, we need to know what the automorphisms, the multiplicative automorphisms, are the ones that we're after. What do they look like for ZP? And there's a very nice proposition, it's well known, that they are the qth powers, and Q has some constraints on it. It must lie between 1 and p minus 2, and it has to be relatively prime to p minus 1. And those Qs, if you identify them, are exactly then the automorphisms of the multiplicative structure that we need. So as a very simple example, if we take, I should have said here, but if we take p equal to 5, then, and that's the construction we're going to look at for Z5, the Qs are allowed to lie between 1 and, that should be p minus 1, sorry, 1 and 4. And we look at all the elements that are relatively prime to 4. And in this case, our options for Q are 1 and 3. So those are the 2 automorphisms that we may use to construct the near vector space that we're interested in. So as a very simple first example, we're going to take 2 copies of Z5, and that's going to be our V. The scalars are also going to come from Z5, and according to Van der Waals' theorem, we are going to define the scalar multiplication such that we apply the multiplicative automorphism before we multiply it in. So the pair that I've chosen is 1 and 3. So of these numbers, I'm going to take both of them. And of course, x to the 1, or in this case, alpha to the 1, if we apply to the scalar, would just be alpha. So we get just the normal multiplication, which is alpha x. But in the second component, instead of multiplying just by alpha, for instance, alpha y, we are going to apply the cubic automorphism. So we're first going to take alpha, cube it, and then multiply by y. So what we've done is in the second component, we've perturbed the multiplication. And by doing that, we lose one of the one of the distributive laws, and we get our first example of a very simple proper near vector space. And I say proper because it is not a vector space. And why is it not a vector space? The distributive laws won't both hold. So also for clarity, if you think of a vector space, there are 2 distributive laws that must hold. The first one must be that alpha times, in brackets, v plus w should be alpha v plus alpha w. And the other one is that if you apply alpha plus beta to u, then alpha u and beta u must follow on the right-hand side. Now, we have that alpha applied to V plus W would be alpha V plus alpha W. We have that distributive law. We don't in general have the other one. That's the linearity that we lose. So if we go through the steps of finding the quasi-kernel, remember the quasi-kernel, if I just scroll up, are the elements with this property that if I take any alpha and beta in A, I can always find a gamma A such that I can write alpha X plus beta X equal to gamma X. Now, those elements, if you try and identify them, turn out to be all the elements in the first set, which are all the elements A0 or all the elements 0B. So in order for you to have that property of being able to write that linear equation down, either you must have A0 elements, so and 0, 0 isn't the quasi-kernel, so you may wonder if 0, 0 is allowed, it is. But 1, 0, 2, 0, 3, 0, 4, 0, they will all satisfy that property. And in the same way as 0, 1, 0, 2, 0, 3, 0, 4, all of those will also satisfy the property. And so these are the elements of the quasi-kernel. And certainly not all the elements are in that union. So the quasi-kernel is a proper subset of the set V. And I'm not going to go into the proof of, why there is a generating set in the quasi-kernel. But what I can share with you is not difficult to check is that as you would expect for vector spaces, the set 1, 0, 0, 1 is a basis. Obviously, each of those elements sit inside the quasi-kernel, and they are able to, just with the vector space Z5 over itself with the usual multiplication, they generate all the elements. And so they serve as a basis, and we will also speak of the dimension of this near vector space being 2, as it would be for its counterpart, which would be if we took Z5, 2 copies of Z5 over itself. So now you might wonder, why is this interesting? How many things break? Why do we even care about the distributivity? That's all coming. But one concept that already highlights the difference between vector spaces and near vector spaces is the notion of regularity. Okay, I use the star notation. I should also just mention, instead of writing each time a set without 0, I introduce the star notation just because it's a bit simpler to work with. But a near vector space is said to be regular if any two vectors of the quasi-kernel are compatible. And the property of being compatible means if I take any two vectors in the quasi-kernel, any two arbitrary ones, I can always find a non-zero scalar lambda such that U plus lambda V is back in the quasi-kernel. So it's a type of closure that we have here, that the sum will always be back in. And what Andre proved, and we call it the decomposition theorem, is that every near vector space is either regular itself or it is non-regular. And in that case, we can always decompose it into maximal regular subspaces. And so we have a way to always decompose any near vector space into regular parts. So Andre referred to these regular parts as the building blocks of near vector spaces. Now, why are the regular near vector spaces so important? They are the subspaces, or the vector spaces if you want, that are the closest to vector spaces. So when we study their properties in terms of what we expect, the regular near vector spaces are the ones that behave like we would expect on most things if you check them. The non-regular ones are the ones that I like to refer to as the weird and wonderful ones, because they are very strange, and we are constantly discovering more strange things that can happen when the near vector spaces are non-regular. But what is important to share, which I think is very special about these structures, is even though they are less linear than vector spaces, this theorem gives us a tool to always decompose them into subspaces that do behave like vector spaces and are maximal. And so maybe I can just say here, what it means is you can take any vector space V and you can decompose it into a direct sum of maximal regular subspaces, and each of those subspaces have this nice property of behaving like a vector space. So this decomposition is also very strong. It's unique. It's called the canonical decomposition. So basically, the theory of near vector spaces is largely reduced to understanding the regular spaces and then how they interact with each other. And that is predominantly what our work has been, because if I give you a near vector space, either it's regular or decomposes into the regular parts. And so far, what we've seen is that the regular parts are very close to vector spaces in preserving their properties. You may wonder, I mean, I mentioned to you with vector spaces, the quasi-kernel is always the whole space. Is that a condition for regularity? Not in general. So it is true that if V is equal to the quasi-kernel, then V will be regular, but the converse is not true in general. In our case, which is for these constructions over ZP, the two will always be equivalent, but in general, they're not. So when you look at more general constructions from near fields, then certainly this is not true in general. Now, why does regularity matter? As I shared to you, it seems that the regular near vector spaces are the ones that are very well behaved. And since they are most like vector spaces, we have a very good understanding of what they behave like in various settings. Some people might think it makes them less interesting, but it does certainly play a role in studying near vector spaces. So as a comparison, just if we take our example Z5, 2 copies of Z5 over itself, and we take the normal multiplication, which is just multiplying any tuple by the scalar entry-wise, so coordinate-wise, versus the one I showed you where we multiply normally in the first component, and in the second component, we first cube the scalar before we multiply. I thought it might be insightful just to compare for you. So for a vector space, the quasi-kernel would be the entire set, the V, the set of vectors. We saw with a near vector space, the quasi-kernel is a disjoint union that we can write down. The basis stays the same. The set 1001 will do what it needs to do in terms of generating, and it's a subset of the quasi-kernel, which is required for V to be a basis. Both of them have dimension 2. The vector space is regular. If you went to check the property for any two elements, it's true that U plus lambda V, you can find a lambda, non-zero, such as U plus lambda V is back in V. That just follows from the closure of scalar multiplication and addition. So it is regular. So there's no proper decomposition. It is regular itself. But for the near vector space case, it's not difficult to check that if you took two vectors and you added them, for example, if you take the vector 1, 1 and 1, 2, they are vectors in the vectors. Sorry, no, let me rephrase that. You take two elements of the quasi-kernel, 1, 0 and 0, 1. There's no scalar that is non-zero that exists such that 1, 0 plus lambda times 0, 1 would be back in the quasi-kernel. So it's definitely non-regular. But if you composed V into the two parts, and V1 is the part where all the elements of the form A0, and V2 is the part where all the elements are of the form 0B, just like the quasi-kernel. So these cells here, A0 and 0B, these sets actually become V1 and V2 according to Andre's decomposition theorem. Then V1 is a maximal regular subspace, and a subspace is just as you would expect for a near vector space, a subset that is closed under multiplication and closed under scalar multiplication. V1 would be regular on its own, V2 would be regular on its own, but V as a near vector space would not be regular. And so that just gives you an idea of some of the subtle changes that we see between these two. So what makes them so weird? At the moment, you might not be convinced that they're weird. We've just changed one coordinate. We lose the linearity. Why is that interesting? Who cares? What can you do with them? So this is something that is really interesting that we've discovered that I want to share with you and then hopefully motivate to you why I think it's so interesting. So if I asked you for a vector space, is it possible to find a single vector that can generate the entire space? So say I give you a vector space of dimension 2. If I asked you to give me one element that would generate the entire space, you'd think I don't understand enough about vector space theory because it's impossible by the laws that govern dimension and all the results attached to that. So we asked the same thing. In fact, we mistakenly come across this. The question wasn't, is there a V that can do this? We were actually looking at a different question and then discovered that there are some Vs that can do it, which is very interesting. And so with a student who was actually at the time based at Ames, he's an alumni from Ames, we defined and wrote some papers on this. And this is the definition that we need because it is possible. If we can find a V in our near vector space V such that the span, again, same notion as with vector spaces, it's all possible linear combinations of a V. Is it possible for that to give you the entire near vector space? Then V is called a generator of V. And of course, for vector spaces, this is impossible. Is it possible for near vector spaces? Yes, it is. Sylvie Sanon, who's the student I spoke of, we discovered that for ZP, for near vector spaces constructed over ZP, and we proved a theorem of what those generators would look like. But we didn't have all of them. So the theorem left out some of the candidates for the generators. So with another collaborator, Nancy Newdower, who I still collaborate with, and we're currently working on a project studying the matroid properties of near vector spaces, we proved the following theorem. Again, I'm not going to bore you with the details, but just to say, if you take any element that is outside the quasi-kernel and has a non-zero element in each one of its components for this type of construction that we've looked at. I should also say it's a class of near vector spaces for which this is true, and it's all those where each scalar multiplication is distinct. So they all have to be distinct from each other. So you couldn't have that, for example, if you take 3 tuples, it's not the case that if you took the multiplication to be to the power 1 in the first and to the power 1 in the second and then cubed in the third, this theorem doesn't hold in that context. It specifically holds for the class where, like we did now, for the first component, we used q equal to 1. So the scalar multiplication was the normal multiplication. And in the second one, we took the cubic power. So there are 2 distinct multiplications that define. So if you have n distinct multiplications and the near vector spaces of dimension n, we know that any element that has non-zero elements in its coordinates outside the quasi-kernel will act as a generator for the space. So going back to our small little example and applying this theorem to it, we discovered that the element 1, 1 is a generator. It's not the only one. Any of the elements outside the quasi-kernel with non-zero elements will be able to generate the entire space. And note that this doesn't take away from the basis. We still speak of this near vector space as being of dimension 2. We know that its basis is a set that is the elements 1, 0, and 0, 1. But outside the quasi-kernel, we have elements that can entirely generate the space. Andre didn't define dimension any different. It didn't affect the notion of dimension at all. In fact, I'm not sure that he knew that this was possible, that the generators exist, but they do, and they work together with a basis. So we don't change the theory to accommodate. We take note of them and we adjust accordingly. And so this is very weird to have a structure like this, but I think this is exactly the structure that we need to capture some of the nonlinear behavior that at the moment in many of the practical sciences we are not able to capture quite yet. So I thought I would just draw you a little picture. So this is what our space looks like. So we have this set inside the quasi-kernel. It's a subset of V, the white square representing V here. We know that 1, 0, and 0, 1, what I circled in red, is our basis, the usual one that operates exactly like we know, nothing shocking about it. But in fact, I circled 1, 1, but all those elements on the outside actually have the power to generate the entire space on their own, which is very weird. And so this is something that we've discovered. And again, it's not for all near vector spaces, but for this particular class, it's something really strange that has come to light. All right, so why am I interested in near vector spaces? So when I first was starting, I always used to feel very insecure because I knew at some point there would be someone in the room that says, why would you be interested in this? Where are they useful? What do you think you're going to do with them? And really at the time, I had no idea. I just thought they were really interesting. I liked them, and I thought that's enough. And sometimes it is. But I'm very proud to say that I think I have some ideas, and they have proven to be very useful and very interesting. As I said, I have collaborated with mathematicians in different branches of mathematics, geometry, model theory, matroid theory are some examples. And recently, some of my ex-colleagues have also taken this work into category theory and discovered some very nice properties that they have learned of while studying these structures. So they've been very interesting to work with. And the geometric exploration is something that is still very much open. So Andre's motivation for defining near vector spaces in the way that he did was motivated by his work in geometry. And he's very well known in geometry if you searched up his work. And his idea was defining them to give access to some new structures in geometry. And that is also work we've been revisiting just to see what else can be added now since we understand more of these structures than perhaps he did at the time. So now I want to introduce you to a finite linear game, which is something really fun I discovered when I was teaching first year mathematics. There's a book by Poole called An Introduction to Linear Algebra, and we use this book to teach the first year mathematics. And at the end of the chapter on systems of linear equations, he has this lovely application where he applies ZP to solving a finite linear game. And at the time, I thought, okay, this is interesting. What happens if you replace that vector space with a near vector space? And this is what I want to show you, that the near vector space can model weird behavior, but in a very organized way. And then at the end, I'll tell you where I think that they're going to be useful. So a finite linear game is a problem that involves a physical system with only a finite number of states. So that's why ZP is perfectly suited for it, which can be altered by applying certain processes and resulting in a finite number of outcomes. So we've got finite number of states, finite number of outcomes. ZP is going to be our vehicle. So these types of systems feature in computer science, and they also feature in natural science, where you have a certain number of states that are allowed for a particular object. But they're also very prominent in games, in game theory. So we generalize the idea here and restrict the number of finite states to ZP for P of prime. For us, we're going to focus on Z5 since we have the near vector space structure above, and I'd like to attach it to the work that we did there. So what we're going to do is we're going to have some light bulbs. They're very special light bulbs. They've got P different states. So I like to think of the possible states as colors. So you have P different colors. State 0 would be that the light isn't shining. 1 could be red, 2 could be blue, green, and so forth. And what we're going to do is we line the light bulbs up. And at any point, we can, of course, use a vector to capture the state of the light bulbs. So we can record. So we can say that the value 0 is a certain color, 1, as I said, and then we could use a vector as the vehicle for recording the state, or in this case, the color of each light and keeping track of it. So we have these V's that keep track of what color each light is. And we can, in the game, use a vector Ti to be the initial configuration. It could mean that all the lights are off, so then we would just have zeros in the column. Or you could actually start off playing this game with a particular configuration. For example, the first light is yellow, the second is off, the third is green, and so forth. And then you also want a final configuration, which is you choose some configuration that you're interested in, for example, red, green, yellow, etc. Or you could go for, let's see if the final configuration is all of them having a certain color. So you can play around with it. The setup is that each each light bulb also has a switch associated with it. So, for example, in our case, if we have 4 light bulbs or 5 light bulbs, we're going to have 5 switches, and each switch is going to tell us in vector form what it does. So, for example, switch 1, its first entry will tell us what it does to light bulb 1. So if it was state 1, then it would mean that it's color 1 and so forth. So, the entries that are 0 would mean that that switch leaves a light bulb in that position untouched. It doesn't change its state. What's also important is that the light bulb changes states consecutively or sequentially, which means we can't have the light bulbs normally jumping around, but the state 0 goes to 1, goes to 2, goes to, and so forth until you get to P minus 1. So we work very sequentially. So each change brought by a switch actually corresponds to a vector sum. So the final configuration would be the initial configuration plus the vector that represents the switch. And in this way, the vector addition actually keeps track of the changes that happen after you press each switch, and you update the TF with the configuration that resulted in. So this extends so that the final configuration is then a linear combination. The final configuration is your initial configuration plus then scalar multiples of these switches. And why scalar multiples? Because the scalar multiples represent the number of times you press each switch. You could choose to start with the initial configuration, press the first switch twice, then C1 would be 2. You may only choose to press SM, for example, once, then its scalar would be 1. So you can keep track of how many times you want to press each switch. It's not required that each one only gets pressed 1. So once we understand this setup, we can associate a vector space with it because we've got a finite number of states, so ZP makes sense. We have a certain number of switches, so we can take ZP to the power M. And we understand that the vector addition keeps track of pressing the switch from one configuration to the next. We also understand scalar multiplication now because we can associate it with the number of times a switch gets pressed. And that just results in multiplying the vector, the switch vector, by the scalar and doing it component-wise. And this all works very nicely, and it allows us to ask questions like, given a certain configuration, initial configuration, is it possible by using the switches that I've defined in a particular way, pressed in some sequence, to get to a final configuration? And what we will see in even our example, and if you ever get hold of the book as well, that not all configurations are possible. So you can actually use linear systems and solving linear equations to say which configurations are possible given an initial configuration and switches with a particular function. So we're going to set up 4 lights to keep it very simple. We're going to call them A, B, C, and D. Each of these lights have 5 possible states, but we're going to have 4 different colors. So 0 will be no color, and then 1, 2, 3, 4 would each have a different color. And each switch has a different description. So switch A is 1004, B, C, D each have some numbers, elements of ZP associated with them. And just to give you some insight, so A, if we say that A is the switch 1004, then what that vector is telling us is that A will change the first light bulb to the color 1, which I've chosen to be yellow. it's going to leave light bulb 2 and 3 unchanged, whatever state it was. We're going to start with the state of having them all switched off, which means all of them would be zeros. So it would take the first one to color 1. It would leave the middle 2. If your initial configuration wasn't 0, it would just leave whatever the middle 2 colors are as is, and it would add 1 to the next. And then for the last bulb, it would take it to color 4, which in my case is red. And now I can ask, so each of these you could draw what their outcome is and what they do. Our question is going to be, if I start with all the lights off, all the light bulbs off, that's my initial configuration, 0, 0, 0, 0. I want to see, is it possible by pressing these given switches that I've defined a certain number of times, so a linear combination, such that I can get the final configuration of 1313. And of course, 1313 is a color sequence according to the way we've defined this problem. It amounts to solving the following system. So it's a very nice system. It's a coefficient matrix. You learn how to solve this in the first year. And you can see that I'm not going to ask us to solve it, but it can be solved. And in fact, we get that you C1, which is the number of times you must press switch A, has to be 2. So you press switch A twice. You press switch B 4 times, and you don't press the other 2, and then you'll get exactly this configuration 1313 in the lights. Not all configurations are possible. So that is just the problem from pool. But now I want to take you into the world of near vector spaces. So we're going to stay with exactly the same setup, except when we press a switch, which is our scalar multiplication, we are now going to take the scalar and first perturb the multiplication. And one of the multiplications we learned was take the scalar and raise it to the power 3. We're going to do that in each component. So when we multiply, we are first going to cube the scalar and then multiply it in. And what does that do to the system? What does it do to the switch? And in the previous example, a switch would work sequentially. What is the situation in this particular setup? And now our system looks slightly different. When we try and find the linear system that we need to solve, we have these cubics, but we know that cubic roots exist in Z5, so it's still a system that we're able to solve. And in this case, for example, now with this cubic multiplication, we also find that we can get this particular configuration by pressing the first switch. It's a different set 3 times and 4 times, and then leave the other 2, but we're still able to solve it. So what is interesting is that in this situation, when you press a switch, it's no longer the case that pressing a switch n times is the same as n times k. In fact, in this case, the switch behaves the same way as in the first example it is pressed. So the first time you press it, yes, it behaves like we would normally want it to behave. But from there on, it's almost that it remembers where it was and keeps moving through the system. And so what this shows us is that these structures are able to keep track of the linear behavior, but also behave very differently. And this is why I think there's a lot of scope for applying them in very practical problems. I haven't found the problem yet, and I always share this talk hoping that there's someone listening who's got some ideas of how to take this further and where to take it further. But I do believe that near vector spaces are the vehicle for understanding nonlinear behavior. And in many of the practical sciences like ecology and biology, often there are assumptions made that a system behaves more linearly than it actually does, just to allow modeling to take place or mathematical methods to be applied, like linear equations, for example, in a linear setting are much easier. But near vector spaces give us an algebraic structure that capture things that are nonlinear, but in such a way that we still have a linear component that's familiar to us and that we can work with. And more than that, Andre's theory allows us to take something that's very nonlinear and decompose it into linear parts. So I close off with just an example just to show you that you get a very different solution here if you wanted to solve it, but it is solvable. And just to show you in the first example, if you compared it, pressing A twice would result in 2A. In this case, pressing A twice is definitely not the same as 2A. And so you can see as you press the switch more and more, you're no longer working with the multiples that you would normally have. And so we thought of this as the switch remembering where it stopped, which may seem a bit strange to think of it like that, but it's just that the switch, the multiples of the switch no longer behave in the way that we expect them to. So why this is useful, I said to you, I really believe that near vector spaces give us a way of capturing nonlinear finite systems. They are very useful. So I'm hoping that in a future talk, I can tell you that they definitely were very useful. We just found the application. And then in closing, I'm almost done, but I just always like speaking about the place where I'm from as well. So we're based in Cape Town in South Africa. We're part of a network. It's the African Institute for Mathematical Sciences. We're the first center that came into being in 2003. We celebrated our 20th anniversary recently. And our mandate is to train top scientists across Africa. So we have many students applying for a structured master's degree. Normally we have about 2,000 applications. We choose 30 at a time. And they come and do a master's degree in mathematical sciences with us. And we train by having lecturers from all over the world flying in to teach in blocks for 3 weeks, 30 hours course. And it's a really special place. It's a very diverse environment. People are flying in and out all the time, visitors from all over the world. We also have a very active research center. So I invite you to visit our website and learn a little bit more about each of our researchers and the work that we're doing. And just to extend a warm invitation to all of you, you are welcome. We're a block away from Muizenberg Beach, which is one of the top surfing locations in the world. So I want to throw that in as well. And we have a surfboard that Ames branded. So we're a group of people who really have a deep sense of purpose, but we also really love what we do. So please think of coming to visit us and seeing if you can contribute to our very special institute. So thank you for the opportunity.
Okay, thank you very much, Professor Karin Dres-Hall, for your very interesting talk about near vector spaces. And also thank you for this very nice invitation, of course, for the mathematical community to visit the African Institute for Mathematical Science in South Africa. So, are there questions for Professor Karin Dres-Hall? Kabe, you have question?
Yes, if I may have a question. And actually, I have a lot of questions. First of all, thank you very much for a very interesting talk. This concept is new to me. Well, as a topologist, the first question that came to my mind, is it possible to define topology compatible with these spaces, like topological vector spaces? Is it possible?
So it hasn't been done. I mean, no one's explored this. This is the one area I haven't gone into yet. I have no idea, but that's a very good question to ask. So that's one of the things I haven't explored. So definitely it would be worth exploring. I don't have the answer for you. I'd love to know.
And then also the follow-up question is that if it is possible to define like topological vector spaces, the next question is it possible to define, to build differential or integral calculus on these spaces? So it can be very completely new things. So
Yes, no, definitely. And there's many open avenues to take this into. So those are very good questions. I don't have answers for you, but they're valid questions to ask for sure.
So no work has been done yet on this.
No, not that I know of. So we have a
Well,
very active. Sorry.
Yeah. So I'm interested in direction because I am working on on locally vectors, locally convex vector spaces. So I am very interested in building calculus on locally convex vector spaces. So I was wondering if it is possible to generalize using these new generalization of vector spaces.
Yes, no, I think it's a very valid question. I don't think anyone has looked at it yet, and my reflex reaction would be yes, it would be possible, and they'd be very interesting, but I might be wrong.
Well, just
yeah, it's a very
something
good
that,
question.
yeah, sorry, that's just something that comes to my mind first, that as we lose linearity, so if we want to build differential calculus, the derivative will not be linear operator, right?
Yes.
So
Yes.
we will need to build completely new different calculus.
Exactly. Yes. That is true.
Wow. So maybe I don't know. It is new to me. Maybe I'm interested to maybe we'll think about it.
Yes, and you're welcome to email me as well. I'm always looking for new projects to look at, or even if you just want to chat about it, I'm happy to do that. So please reach out.
Thank you very much, very much. Thank you very much. If I have come with some new ideas, I will contact you. And thank you very much. It is very new to me, and I think for many people who work on topological vector spaces, this is something completely new. It is a generalization. We can do many things new. Also,
Definitely.
the huge works, huge new works and open works. I imagine.
Yes, definitely.
Thank you very much. It was very insightful for me. Thank you very much.
Thank you.
Okay, Kabe, thank you very much for your very enthusiastic questions, of course. It's
Great,
interesting
thank
to
you.
see that among our attendees, we have people that were very enthusiastic about your presentation, Professor Karim Derez.
Good, thank you.
Are there more questions for our speaker? Sorry, I think I have just a curiosity, but I think it's maybe related with the linear algebra, right, of vector spaces, because sometimes, let's say one have diagonal operators, and with diagonal operators one can construct bases, right, of
Yeah.
vector spaces. Question is if these notions of linear algebra maybe have been explored in this setting,
Yes.
right?
Yes,
Eigenvalues, eigenvectors, etc.
Sure, very good question as well. So I have a colleague who was at Stellenbosch, Sophie Marquez. She's now in Spain, I believe. And she has started working on developing a theory called near linear algebra. So looking at exactly these questions that you're referring to now, like what happens with all the, if you take a first year book on vector spaces, what happens when you actually start talking about norm, when you actually start looking at all those concepts and how they change in the space. So they've started a project on that, and there's already a paper on that that's available. Very interesting paper to read. And so anyone who's interested in developing that material could look at that as a starting point. But there are some very interesting questions there as well.
Thank you very much. Thank you very much for this information, of course, very interesting. Yes, because then there is a lot of functional analysis, right, that one could think about how to generalize and so on, right? So
Yes, and that's another area that hasn't been explored is in functional analysis, for example. So there's still a lot of work to be done. So anyone who's looking for an area to explore, there is a lot of open questions still available.
okay. Thank you very much. I think Professor Karinderes Howell, our attendees, were very happy with your presentation. We don't have more questions. So
Thank
again,
you.
just thank you very much for accepting our invitation. We were in contact because now we have a common project with one student in ICMAM,
Definitely.
Latin
Yes,
America, with
definitely.
one of
Thank
your
you. And thank
students.
you for the invitation. I was very excited to be part of this. So thank you. It's very nice.
Thank you very much. So I really invite you maybe to a closing ceremony, just if you can't, because there we are going to launch today one initiative of ICMAM in Africa related with our colleagues in Ghana. So maybe of
Okay.
your interest. And you
Nice.
are welcome, of course, to join.
Okay, thank you. And that's later.
Right, it follows a plenary talk. After the plenary talk is the closing
Okay.
ceremony.
Okay, I'll do that. Thank you. Thanks for the invitation.
Thank you very much. So, Manuel, please. Okay.
Thank you very much. Dear Professor Joaquim Toft, are you in the room with us?
Yes, I'm here. Can you hear me?
Yes, we can hear you fine.
Hmm?
It's a pleasure to have you here. Could you please try to share your screen to check everything is working fine, please?
Yes, absolutely. Just a moment. I share my file, okay?
Okay.
So not the whole, this is enough, yes, I think.
Yes, we can see your presentation just fine.
Is it better now or does it change anything?
It is bigger right now. Yes.
Is this
Thank
fine?
you. Yeah, it works. We can read it fine.
I can also make it even larger if you want to.
I think that's it shows the whole screen for us. I mean, this full screen.
Okay. Perfect.
Thank you very much. Thank you, Professor Joaquim Toft, for joining us today and accepting our invitation. It is a pleasure to have you here as a plenary speaker with your presentation, Convenient Norms for Modulation Spaces with Applications to Pseudo-Differential Calculus from Linnaeus University in Sweden. The time is yours, Professor. Thank you very much for your presentation.
Thank you very much for this. I see that I will just change it a little bit. Let's see now. Can I just do it like this? Now I think it's better. Okay, and then. So I start my talk now, or?
Yes, please.
Okay.
Feel free to start whenever you prefer.
Okay. Well, thank you very much for this. I'm very honored to be a plenary speaker of this conference, and thank you very much for this very nice conference. I have not been able to join all talks, but some of them, okay? And I can also see my old friend nowadays, Professor Cardona here. I hope everything is fine with you, okay?
Hello, Professor Toff. Nice
Yeah.
to meet you. Nice to meet you.
Nice to see all of you now, okay?
Yes.
Yes, so this is a little bit about my talk, Convenient Norms for Modulation Spaces. I'm not sure that all of you have seen about modulation spaces, but somehow this is in comparison with, this is of course also about a special case of topological vector spaces. Perhaps not so much difficult topologies compared to if you have, for example, inductive limits or projective limits of Banach or Fréchet spaces, I mean, especially inductive limits. So this is a little bit more easy. It's, of course, we are encountering, as we will see, something called quasi-Banach spaces. So the plan of, why can I not do it now? I cannot. What happened here? Okay. Here perhaps. Okay, sorry. This is the right arrows. So this is the plan of my talk. So I'm going to talk about Gelfand-Shiloh spaces, good example of topological vector spaces, about classical modulation spaces, a more general class of modulation spaces, and also applications. So then we are talking about applications, especially in pseudo-differential calculus and so-called Toeplitz operators, which are the same more or less as localization operators in our world, okay? And you can also see that the talk from the line here below that this is also done in collaboration with Christine Pfeuffer and Nenad Teofanov, okay? And everything is actually based on a recently published paper here, okay, which has almost the same title as the talk. So it was just recently published here, 2026. And of course, you can see this is not a very short paper. It was more than 80 pages long because we needed a lot of room to prove our different results, okay? So now I come to the mathematics. So we all remember the definition of the Schwarz space, okay? So this is spaces, I see. I can see I had this right. We have this definition of the Schwarz space, and this is well known for you. It should decay faster to zero at infinity than any polynomial, as well the same thing with its derivatives, okay? But if we now talk about Gelfand-Shiloh spaces, then we have some more detailed information about these objects, okay? So what we do here is that we keep this expression, norm expression here, but we put some sort of more global conditions. One can say that this here should be bounded by a constant depending on alpha and beta. But here we specify this constant, so we can take that this object divided by this with factorials, etc., and supremum of this should be less than infinity. One can think about that if you take sigma here to be less than equal to 1, then we get analytic functions. So these kind of conditions, they are suitable when you want to discuss not only test functions, but also analyticity, okay? There are also another type of Gelfand-Shiloh spaces. Here in this definition here, I prefer that this should be true for every h. But if you take that this should be true for some h, you get another scale of spaces. Actually, in a topological sense, very different. So for example, these sigma spaces, they are Fréchet spaces, but these Romieux type spaces, they become inductive limits of Banach spaces, okay? With worse topology, okay? You cannot take this S and sigma too small. So if you should have non-trivial spaces, then S plus sigma here must be strictly larger than 1. Otherwise, they just contain one element. And you get the corresponding distribution spaces. You just, well, they are the dual of this, or let's say the strong dual of sigma S sigma. So that's it. And what is interesting here is that we have this kind of embedding properties. So if you increase S and sigma, you increase the Gelfand-Shiloh spaces, but they never become as large as the Schwarz space. On the other hand, the corresponding distribution spaces, you have the reversed order. So you can have a lot of, how to say, larger distribution spaces than the tempered distributions here, okay? So that's about these objects, okay? One can say, for example, that if you take S here to be less than equal to 1, then you can have exponential functions in your distribution space, which is not possible in the set of temporal distributions. And we also, if S and sigma are equal, we just have one index. And actually, as we will see in the next slide, this gives so-called Fourier invariant spaces. So then we can use the Fourier transform, and then they will be invariant under this Fourier transform. So that's it, okay? Gelfand-Schirler space and Fourier transform. So we use this definition as our Fourier transform. And then we have a local Fourier transform where you just localize your functional distribution first and then apply the Fourier transform. This gives some, in signal processing, this will give some sort of a locally in time frequency resolution of the signal. So that's a little bit about that. And what one can prove then is that the indices S and sigma, they are basically swapped under the Fourier transform. So of course, if they are equal, then they will be the invariant under Fourier transform. And the same thing with their distribution spaces. There are a lot of interesting characterizations of these Gelfand-Schirler spaces. Actually, this is from about a little bit more than 30 years ago. One has that F is in this sigma S sigma, if and only if the function and its Fourier transform obey these kind of estimates, okay? And as you remember, we had for every h greater than 0 when we define this sigma S sigma. And here, for this reason, actually it becomes for every r greater than 0, you should have this kind of estimate. So this means that you have more requirements how they should decay towards 0 at infinity compared to the Schwarz functions, because there was just a 1 over polynomial decay, but here is actually an exponential type decay. But using the short-time Fourier transform, we can actually put these two inequalities into just one. So we have that F is in sigma S sigma, if and only if you have just this condition here. And this should be true for every r greater than 0, okay? So that's it. But also an advantage with the short-time Fourier transform is that we can actually not only characterize the test functions, sigma sigma, but also their distributions by a very similar condition, but we have to change this minus r into a plus r. And also in the for the test function is for every r, but here for the corresponding distribution, it's enough that you have this estimate for some r greater than 0. Okay. So please stop me if you feel that you want to know, if you feel that it goes too fast or so, okay, and just come with questions if you so want, okay? I continue with the next slide now. Now we come to so-called modulation spaces. Actually, the basic idea with let's say the basic idea with Lebesgue spaces is that you apply some sort of a norm on the function themselves, okay? The basic idea with the modulation spaces is that you first form this short-time Fourier transform, and then you apply a norm. So F here is in this modulation space. It's a classical modulation space, MPQ with weight omega. If and only if this kind of expression here, when you integrate, you take an LP norm with respect to x and LQ norm with respect to xi, and this should be finite. This will actually be defined an expression. We just denote it in this way, okay? And if P and Q are at least 1, this becomes a norm. But if P and Q is allowed to be less than 1, or one of them are less than 1, it becomes a quasi-norm, but not a norm, okay? We come to this kind of concept of quasi-norm a little bit later, okay? Of course, it's nice to have a little bit abbreviations of if P and Q are the same, we just put P instead of MPP. And also an important case is when you have trivial weights, omega is equal to 1. Then we just omit the index here with weight, okay? So that's it, okay? Of course, we could see here that here was a weight function. Can we do a good calculus for all weights? No, well, no, not so easy at least. We prefer to usually put some suitable conditions on them, okay? So first we have this condition, omega is called V moderate if it satisfies something like this, okay? And PE is the set of all moderate weights, okay? But without this index E, just a moment, I have to close my door for a moment. Jag håller före då. Hej. Sorry. This is the set of all functions that are moderated by polynomials, okay? And we will soon see examples on common weights, okay? Because I have soon listed some well-known modulation spaces. What one can prove is actually that if you take omega here, if you take the intersection of all these modulation spaces, MPQ omega, with weight in this big class PE, intersection gives sigma 1, while the union gives sigma 1 prime. Okay? What happens if you take the smaller class with just polynomial type weights? Then one can actually show that the same type of unions and intersections will give the Schwarz class and the set of temperate distributions, okay? So in this way, we can actually somehow get almost all kind of continuity properties in this distribution theory, at least when we are dealing with, let's say, distributions that are somehow Fourier invariant by using these modulation spaces, okay? But especially we can see here that if we want to stay in the usual distribution theory, then we should just have weights that are moderated by polynomials. Okay. Some properties. Well, actually, if you take here this bracket function like this, that you recognize, for example, when you're discussing Sobolev spaces or Besson spaces, and perhaps we put then modulation spaces when we're using such kind of weights. We can call it MPQST when you have these exponents T and S here, okay? If you take this T to be 0, but not S, then M22 will give us the somehow standard Sobolev space defined on the whole RD. If you instead take the other to be 0, but still the exponents to be 2, then we get a weighted L2 space, okay? So that's a little bit, so we can then that way regain a lot of our, how to say, some of our common Hilbert spaces, okay? We get a lot of Fourier invariant spaces. For example, if this omega 0 constructed from omega here should be the same as omega, then it follows that the Fourier transform is taking MPP of omega into itself, okay? But otherwise, if they are not necessarily the same, we have at least this kind of relationship, okay? In a good class of this phi here, it is the window function that we had in the short time Fourier transform. It turns out that there are a lot of invariance properties in the choice of this phi here, okay? And so on. It has also, in the case that we have P and Q greater than or equal to 1, actually then one can show that our classical modulation spaces, they are Banach spaces. Then you have also good duality properties, very natural one, similar to what you have in Bessel spaces and for Sobolev spaces or Lebesgue spaces. But additionally, what is somehow nice here is that if you increase the Lebesgue exponents P1, P and Q, then you also increase the spaces and in some sense also decrease the norms. Another nice property with these modulation spaces is that you can also discretize them using so-called Gabor frames. It's somehow a global type of Fourier series expansion, and so on. So, and then you can somehow, if you're working with them, you can then plug it, you can make some sort of finite approximations and plug in everything in computers somehow. Okay. So now I continue here to just explain. So one can say that the theory, if we first take P and so on from 1 to infinity, it is somehow the standard situation, and then everything is Banach spaces, and then it's usually not a so hard situation to prove all these properties. But if you want to go to the general case, allowing these P and Q to be smaller than 1, and then you need more work to prove everything. Okay? So this is really a more difficult analysis compared to the standard situation. So I continue. Okay. And of course, what was done already 2004 by Galpin and Samara, it also works for general weights. But of course, they didn't work with, how to say, the ultra distributions of Gelfand-Schiller type. Just for fun, we can just see a little bit how can we get such an embedding like this, okay? What one can prove about the short-time Fourier transform is that it is some sort of it actually corresponds to reproducing kernels when you're working with analytic Hilbert spaces of analytic functions, okay? So you can see that you have some sort of reproducing kernel here that is also somehow a twisted convolution, okay? If you now put modulus on this and use and put the absolute value inside to get something larger, and also multiply with omega, now remember that omega is V moderate, and using that we can get from this equality, this type of twisted convolution, an inequality of this kind, okay? And what we can do now is that we can apply Young's inequality, and using the fact that, how to say, this phi here should be a good function. This window function should be a good function. So this should not make any problem. So we know that the norm of this will be finite. And using this Young type, this Young's inequality, we get this estimate here. And then we get the searched norm estimate here, okay? So this gives somehow the inclusion. But this is, as we can see here, only working when these exponents are greater than or equal to 1, because we are using some sort of we have integrals here, okay? We will not explain too much about the ideas when we have, when these pj and qj are allowed to be smaller than 1. What you have to do is that you have to carry over estimates into series and finding some sort of equivalent norms on this, okay? But what is essential here is that once you are able to translate a little bit norms into these series, then we are suddenly, we have not continuous functions anymore. Instead, we have sequences. And for sequences, we have one more type of Young inequality that is not working for the continuous Young inequality. And this is that if A is an LQ and B is an LP, Q is between 0 and 1, and P is allowed to be from Q to infinity. Then their convolution is also in LP. So somehow for the discrete case, we have convolutions where these exponents are allowed to be smaller than 1. And somehow with modulation spaces, we can use this to get results also when P and Q are smaller than 1. And in the end, we can get a similar norm estimates as we have here, okay? But it takes, of course, much more time and much more efforts to get it. Okay, as I said in the beginning, we want to discuss not only the classical modulation spaces, actually in focus of everything that was somehow our, how to say, the really big goal. And it was to discuss more general modulation spaces, where we have replaced these Lebesgue norms with more general type of norms. But we are doing this with so-called, not I said norm, but actually it's about quasi-norms, because we want to not only discuss Banach spaces, we want to discuss a little bit broader concept, the quasi-Banach spaces, okay? The quasi-Banach spaces, they are looking very similar conditions as for the Banach space, but the difference is this weaker form of triangle inequality. You can see here that we take everything up to power r. R is between 0 and 1, and you should have this inequality. An example for quasi-Banach space that is not the Banach space is, for example, the LP spaces when P is less than 1, okay? So that's what we have. And now we come to some so-called function spaces, okay? We assume we let M here be the all measurable functions on RD, and we are just working with spaces that are contained in this set of functions. So a quasi-Banach space is called a quasi-Banach function space on RD, if it consists of such measurable functions. We more or less always assume that this B is so-called solid, and this means that this condition, that if we know that F is measurable, and its modulus is less than the modulus of G, and G belongs to B, then this should imply that F belongs to B, and you have this kind of estimate for some C. Of course, this C is not allowed to depend on F here, okay, or G. That's one thing. But in our investigations, we need to assume one more thing about them, and should be that we call them normal. And normal, it should be solid, fine. It should also be translation invariant like this for some weight, but of course the norm can change if we make translations, but it should be possible to estimate like this for some function v here, okay? But we also want that our norm, or our norm b here, could be constructed from a Banach norm B0 like this. Why do we have such a condition? Well, actually, with this definition, we still include our LP spaces when P is less than 1. Okay? So the big inspiration of this construction is coming from that. We want to include these spaces in our analysis. So that's it, okay? We come with some examples. If we take this B to be LPQ of omega. Oh, okay, sorry. Well, this is just an example of how to say what we could have, okay? So this is an example on actually normal QBF spaces when you have this kind of mixed norm space, okay? Okay. Now we come to the definition of our general modulation spaces. First of all, for convenience, but we will see that we can later on actually take a broader class of phi, but for the moment we choose our phi to be, how to say, the standard Gaussian function like this, okay? And then we say that we have an element in our modulation space M omega B if the short time Fourier transform of f with this window function phi times omega, and the norm and the B norm of this is finite. Then we have element in this big modulation space. It's not big, but let's say a general defined modulation space. Of course, by choosing our B to be this LPQ, we get back our classical modulation space. Yeah, so we are, of course, assume that our B is normal, okay? And just to showing some ideas in our analysis, we now assume that V here is just 1, okay? Just to avoid some technicalities. We just want to express ideas. Okay. Another example that is somehow not classical modulation space is Orlitz modulation spaces. To define Orlitz spaces first, we should define somehow Young type functions. So suppose phi here is a map from 0 to infinity to 0 to infinity, but here we allow that it can take the value infinity, okay? So this is called an R Young function for some R. If phi of 0 is 0, phi t1 is greater than 0 for some t1 positive, and we also require that for some positive t, this should also not be infinity, okay? And we also require that this object here should be convex, phi of t up to power 1 over r. Then we can define this so-called Orlet space in this way. So we make this construction phi of this, like this, okay? And we divide this by lambda. What I can say is this, the condition of phi implies that it's actually an increasing function, or let's say non-decreasing function. So what you then, and one can then see that this here is decreasing with lambda, this integral here. So what we do is that we take the infimum over all lambda, such that this here is less than 1. And this will create some sort of a norm, a quasi-norm actually. And if we should have an element in our Orlet space, then this norm, this expression here should be finite, okay? And then the Orlet modulation space is defined in this way, okay? So f is in this m phi if and only if this here is bounded. We can see that Orlet spaces are a more general concept than the Lebesgue spaces. So this would be a larger family than this MP spaces, okay? Okay. Just an example on when it could be good to use something different than the classical modulation space is actually when you look at this entropy functional. This is a non-homogeneous functional, okay? So actually, if you take this Young function to be equal to minus t squared log t squared near origin, then this m phi here will contain all mp when p is less than 2, but will be contained in m2. And I suspect that this is the largest Banach space where this entropy functional is continuous. I can also tell you that this entropy functional, you can find it, for example, when you estimate kinetic energy in a quantum system. And then this f here should be the state function of the quantum system, okay? So then one has that this entropy functional is continuous on all mp and as well as on m phi, but this continues on m2, okay? And so you can see that somehow, at least in this diagram here, this is the largest space that is where this entropy functional is continuous on, okay? Okay. I continue. So what our intention is here is that finding various kinds of equivalent norms for this m omega b, just for increasing flexibilities when you are using them, okay, in different contexts. So what does it include? We want to have as few restrictions on omega as possible. They should be moderate, but that's the only restriction, more or less. They should be moderate, but not necessarily that they must obey some sort of conditions that's called GRS condition, which is a very common condition within time frequency analysis. We want to avoid this condition, the latter one, okay? And of course, we want to be able to choose our window function in as large group of functions as possible. That's another wish we have. These are our intentions. So if you go to the Gabor expansions, you have some restrictions for the these windows. But we don't want to have a lot of these restrictions. Okay, so this is our intentions. Can I just ask you, how long time do I have? I don't remember if it's 40 minutes or 50-minute talk.
You still have 15 more minutes to continue your presentation, Professor.
Okay, 15 more minutes. Perfect. So this is more than enough. It should be okay. Thank you. Okay, so discuss these kind of things. We actually, since we are in the quasi-Banach, since we also want to allow quasi-Banach situations, we need to go to also work with discrete type norms. So first of all, there is a natural way to define a discrete version of this quasi-Banach function space. So if you take a sequence f on ZD, then you can make a function on RD in this way, where this chi here is just a characteristic function of a set, okay? So it's equal to 1 on this set. Here Q is the unit cube, okay? You can observe that if you take the union of these cubes, you get the whole space, okay? And then the corresponding discrete space to B is this one. So you require that this norm here should be bounded, okay? This coincides with L. If you take B to be LP, capital LP, then LB will be the corresponding discrete LP space, okay? It's very natural construction. From this, we now construct something that we want to compare with B space itself, but where we have included expressions that is about this kind of expressions involving sequences, okay? So what we do here is that we split up with this J plus Q. J is in ZD and Q is the unit cube. We split up the whole configuration space RD and then take LR norms on each such object F times omega. And then, of course, we record all these objects into a sequence. You can see here that this really become like this here, really become a sequence with respect to J. And then we apply the discrete LB norm on this. This creates a norm denoted by this W, R, omega B, where this R is of this kind of LR, local norm on these cubes, okay? Yes, so that's what we are doing. What can we say about this construction? Well, this is a very natural analysis. What we can say is that if you take the norms becomes larger if you take R larger, and the largest norm is for R equal to infinity. And if we now take R from 0 to 1, which is our degree of our quasi-Banach degree, how to say, and we also assume that our B is a normal QBF space, okay? Then our this Wiener infinity is contained in this weighted B space. So this is the largest norm, so these are the smallest spaces. But it is also contained in when you take replace this infinity with LR instead. Okay, so the space stays here between, okay? If P is between 1 and infinity, then our Wiener space of order P is contained actually in the set of these Gelfand-Schirler distributions sigma 1 prime, and also contains sigma 1. If you instead take p between 0 and 1, strictly less than 1, then it still contains the whole sigma 1, but now it actually contains elements that are not distributions. This is a little bit about the same thing as if you take LP with p less than 1, not all of these elements are distributions, okay? So we encountered a similar problem here with these sequence spaces. Okay, what could we then prove, me and collaborators, okay? So this is somehow the key result in this paper that I showed in the beginning of the talk. You have your weight, you have your normal QBF space of order, etc. And you take phi and psi in this MR of V. This class is much larger than sigma 1, and especially it contains this standard Gaussian, all Gaussians actually. So what we can then say is that, well, the modulation space that was originally defined with this condition, but for phi being the standard Gaussian, now it's true for all such phi in this large class MR of V. That's one thing. But not only that, actually, if you take p to be any number from R to infinity, instead of using this B norm here, you can use this Wiener norm of order p here, okay? And the new thing here is actually that in the classical theory, especially for Banach spaces, then one has to put p equal to infinity. But here we have a big scale of choices of p. We can start from R to infinity. So this is somehow important and new thing here, okay? And what is also important here is that all these norms that we have written down here, okay, they are equivalent, okay? So what is also shown here is that this M of omega b is also a quasi-Banach space of order R. Also for such a very general B, it is the case, okay? So that's about that. Important steps in the proof. The case when you have this standard Gaussian function is somehow more nice because then we can link this to something called a Bergman transform, and with the Bergman transform you are suddenly with analytic functions, entire analytic functions. And what you can then profit on is actually that you can use the maximum modulus principle and using subharmonic estimates to reach, how to say, good estimates also in the quasi-Banach situation. So this is somehow, then you can prove this result, at least when phi and psi is equal to this, okay? If now phi 0 is equal to this standard Gaussian, we have already proved the equivalence 1 and 2. Here below, we have this embedding properties between W infinity and B omega, etc., to say that we have these inclusions 5 and 6 as well. So what we need to show is somehow the equivalence of 3 and 4 here. So the efforts on 3 and 4 are needed, okay? And this is somehow the big, how to say, a lot of, here we had to make suitable estimates and so on. And one can say that it follows a little bit by passing to these sequences and using discrete norm estimates on this classical thing here, okay? If you make these kind of Wiener spaces, you can also reach, since this is somehow connected to discrete spaces, you can also get something here. You can use this also for quasi-Banach situation. Yeah, so that's it. Applications, okay. The first one is about a conjecture, perhaps not so interesting, but it could also be good to see a little bit how some results look in the theory of modulation spaces. One can see, for example, in the book by Gröchenig, that if you have a short-time Fourier transform, you assume that our f and g are non-zero elements. And then if you know that the short-time Fourier transform is in L1 like this, then one can actually show that both f and g must be in M1. Okay. So this is an equivalent. For quasi-Banach situation, it's more hard to say. From this paper by Galper and Samara from 2004, they conjecture that it should be possible to show the same thing when R is between 0 and 1. What they were able to prove by themselves, it is that if you know that Vg of f is in this small Wiener space, much smaller than this one here, okay? Then one can show that f and g are in MR of V. We were able to improve this and also get an equivalence. So what we could prove was that if we don't need to take this to be this exponent here to be infinity, but p between 1 and infinity, starting from 1, not r, then we have this kind of equivalence. So this, but and we can then observe that we have this kind of inclusion. So we of course cannot promise anything about this larger space here compared to this space here, okay? But what we believe is actually that, so we have a new conjecture, and this is that this result is optimal, okay? Okay, so that's it. And of course, to reach this, we will really heavily use this equivalent norm, okay? Application 2, about pseudo-differential operators and Toeplitz operators, and I take now without weights, okay, to just show ideas. This is I use this definition of the pseudo-differential operators. A is a fixed matrix, and then A here could be different kind of symbols. Then the corresponding pseudo-differential operator is defined in this way. And what you can also define a so-called Toeplitz operator by this formula. And it is well known that you can always express these Toeplitz operators by a convolution, by taking a pseudo-differential operator where you take the Toeplitz symbols convolved by a so-called nice function phi, okay? This phi is constructed from the Virtual phi and psi here. A well-known result, for example, in the book by Gröchenig, is that if you take A in M infinity 1, you get that all these pseudo-differential operators are continuous on these classical modulation spaces. And if you take A in M infinity, which is larger than the other ones, then the same thing holds for the Toeplitz operators. The windows should be in M1. So what we could, and we can just observe here that if you take this classical symbol class, then of all symbols that are bounded together with all the derivatives, this symbol class is a subset of this in all these modulation spaces. So we can of course take symbols in this class instead. By our norm estimates, we can now actually extend this result in the following way. First, we reach quasi-Banach situation. Secondly, we can now say that our operators, they are continuous on these more general modulation spaces. And the same thing with the Toepless operators. So that's it, okay? Finally, but I think you're tired now, and this is just the last slide. One can actually also get some sort of lifting properties on this by using Toepless operators with weights as symbols. But this is somehow also this is a very long story to get these kind of results. This was everything I had to say. So yes, this has some history. So I would just thank you for your attention.
Thank you very much, Professor Toft, for this insightful presentation. Thank you again for accepting our invitation. I will now open the space for questions in the audience. Please feel free to write them in the chat or raise your hand if you want to speak. Please do one.
Professor Prof, thank you very much for your very nice presentation, of course. I was waiting if other person of the audience want to make a question to you also, but actually I have a question, right? Related, I think was slide 13, Professor Toff.
Page 15, okay.
Slide 13, I think.
13, okay, yes.
When you present the boundedness properties for pseudo differential operators, right? Okay. I have a couple of questions. One is this pseudo differential operator associated to this new matrix. This is like a generalization of Weyl quantization, right? So
Yeah, for sure. You can take, if you take A equal to 1/2 times the identity matrix, you get the Weyl quantization.
so you don't need other kind of conditions, right, for your matrix. Is independent of the matrix, these results?
Since you have no weights here, it's not depending on the matrix. But these results, you can also extend these results so you include weights.
Okay.
And then the conditions between the weights then will depend on this matrix. But as long as you are not working with weighted spaces, then it's independent of this matrix actually.
Thank you very much. And also maybe because I have here with me two of my students, Manuel, who actually was chairing your presentation. He works in pseudo differential operators on the torus, and the other organizer, Frederic Opoku, is working in Fourier integral operators. I then want to ask maybe a natural question that is how much you know about generalization of these results for pseudo differential operators to the setting of Fourier integral operators?
I can tell you here that yeah, that's actually a good question. It depends a little bit on what kind of Fourier integral operators you're looking for. For example, you have the conditions on the phase function, for example, so I think that what one can reach result about, I showed you earlier about, for example, of course, with the classical modulation spaces, there are different kind of continuity results for Fourier integral operators. But both when you have, let's say, phase functions that are more classical ones connected to hyperbolic problems, But also, let's say that when you have phase function of other kinds, that looks a little bit more to be closer to pseudo-differential operators. I can also say that if you're working with not this big class of modulation spaces, but let's say with Orlitz modulation spaces, we have now some results on Fourier integral operators with such modulation spaces. So they are, of course, a larger family compared to the classical modulation spaces. But to have this very big class, I think that of course, it cannot be true for the whole class, but the question is what kind of restrictions? Can you have just some minor restrictions? This I don't know yet, okay.
Okay, Professor, thank you very much. Thank you.
But I think that, for example, if you discuss about pseudo-differential operators on torus, I strongly suspect that it should be possible to have some similar results of this kind.
Very, very interesting. Well, thank you very much.
Thank you very much, Professor Toft. Are there any other questions in the audience? Yes, Juan Pablo, please.
Yeah, just one curiosity, if maybe you know some implications in terms of information of the continuity of the entropy functional.
Can you say again, please? Can you repeat? Oh, sorry, about the entropy functional, yes?
If you know if there is some implication in terms of information, because the entropy measures information. So what implication do you have when we have continuity?
Yeah, this is actually a good question. To be honest, I was when I was actually a PhD student, I was focused on that entropy functional, and somehow, and in that situation, I was not so much about. It was very much linked to, one can say, as I said, about. Well, it was actually linked to more questions in a pseudo-differential calculus. But I remember also that it was somehow annoying because in that time I could only think, in that time I was not at all working with modulation spaces. And I remember that, but how about this functional? We are talking about making estimates on L2, but L2, I mean, the function is not continuous on this L2. So I was always a little bit thinking about what kind of spaces should be chosen such that this entropy functional is continuous on them. And I think that I indirectly came to modulation spaces of type MP in that time. And but I could in that time not answer if the entropy functional is continuous on MP when P is less than 2, for example. And I'm not sure that there are any investigations before our paper that shows on which spaces, let's say Banach spaces you can use of this kind, that this entropy function is continuous on, okay? But with our investigations, when we were looking at these Orlitz modulation spaces, we could actually get this kind of, in my opinion, precise space. Perhaps, I believe, the largest Banach space where this function is continuous on. Okay. So this is of course just a conjecture, but when it should more be that when you're working with this functional, perhaps you want to feel confident that when you let this functional act on your space, that it should be continuous on that space, okay? I think this is it should be a little bit more about that. I don't know if I replied on your question, but
Yes, yes. Thank you. I was thinking maybe it is uh, the continuity may ensure that, for example, the entropy do not goes to infinity. So it ensures that the informations, uh, because if you have a great entropy, you have less information.
yeah.
So it guarantees that you have at least information controlled by the initial data.
Yeah, that's of course a very good explanation, because if you now have the continuity in terms of these norms, then you know that if you have something in, let's say this was an M5 space, or in MP, P less than 2, and you know that this is controlled, then you also know, then you have some sort of concentration of the information. That's very good description.
Thank you.
There's something in
Thank
the
you.
chat. I don't know.
Yes. They are asking about this operator in the setting of Besov spaces.
Yeah. One can say that I mean this operator class here, M infinity R, okay, it contains symbols of S00, as we said before, okay, and these type of symbols, they are not the corresponding pseudo-differential operators, except for when you have Besov spaces when P and Q, at least when P, but I think also with Q one should have something. I think about BPQ, okay? These operators are not continuous when P is different from 2. Because this S000, they are containing, for example, S10, which is the classical Hermander class. And of course, if you have the pseudo-differential operators in the class S010, they are continuous on Besov spaces and Sobolev spaces for P between 1 and infinity, okay? But these operators are not continuous on Besov spaces. But if you take classical modulation spaces, you can find embedding properties, I would say rather narrow embedding properties between them and Besov spaces. And then, of course, you can get not very good continuity properties, but at least you can say that it's continuous from a smaller Besov space to a larger Besov space with these kind of symbols.
Understood. Thank you very much, Professor Toff, for your insightful answers. We would like to thank you again for accepting our invitation to present in this Congress.
Mm.
It was a pleasure for us to have you here.
Okay, thank you very much. It was a pleasure for me as well.
Thank you. So right now we're gonna continue with the closing ceremony.
Mm.
So thank you to everyone that attended this ISAAC-ICMAM Analysis in Developing Countries Conference for 2026. It was a pleasure for us to have each and every one of you sharing mathematics with us. So right now we're gonna conclude the event. First, we're gonna have some words from the president of ISAAC, which is Professor Joachim Toft, who just spoke. So please, Professor, feel free to share a words with us.
Thank you very much. I don't know, I prepared a small file, but I'm not sure I need that, okay? I don't know how, if you want a big speech or just a small speech.
You Please feel free. Please feel free to
Okay,
change your words.
I'm free. Okay, well, from behalf of President of ISAAC, I'm very happy about this event. Okay, and it's and this success with this conference. Okay. This is very valuable that you can have this event, and you can also gather a lot of people, not only in, let's say, Latin America, but also from let's say Central Asia, and what I can see also in from Africa, etc. I'm very impressed about this. Okay, and of course. It's important to develop these collaborations and work. And I really, well, as you know, not about 1 year, but about 3 years. There will be an ISAAC Congress. Where? Well, actually in Colombia, yes. With Professor Cardona as one of the main organizers. So I'm very convinced that this will be a success for the development of mathematics in Latin America, but perhaps also extremely valuable for ISAAC and so on. I can also just I can see that ISAAC is growing all the time, more or less. It's we get new, I think, 2 more new special interest group. The latest one was in the fractional calculus. But of course, that ISAAC is growing is fine, but what is even more, much more important is that ICMAM is growing, because this is a really direct interactions in mathematics and connect very important links between different, well, from different part of the world, especially today when a lot of how to say, politicians seems to like war more than peace. I think you have encountered this situation rather recently, not so far away from Colombia. But I think then to have this kind of peaceful meetings without restrictions is between scientists is very important. So I actually prepared some slides, but I think it's not necessary that I should show these slides, because this was a little bit about ISAAC. I think people here know ISAAC well, okay? And I hope that I will see you in new conferences in ICMAM, but also that I will see all of you in the next ISAAC Congress in Xiamen in China next year, okay? So with this, thank you very much for this excellent conference, and thank you for letting me giving a talk and also be a part of this closing ceremony. Thank you very much.
Thank you very much, Professor Toft, for these kind words. We are very pleased and honored to have you and ISAAC as part of this event. Thank you again for accepting our invitations. Now we're gonna give some time for the Uzbekistan Mathematical Society, particularly for Professor Erkinjon Karimov from Ghent Analysis and PD Center, and the Uzbekistan Academy of Sciences, which collaborated with us in this event. Please, Professor, will you be so kind to share some words with us, please?
Yeah, thank you very much. So I'm very pleased to present the Uzbekistan Mathematical Society. I would like to give something happened with my screen. About the Uzbek Mathematical Society. So let me start with some information about Uzbekistan. The beginning. So Uzbekistan is one of the 15 ex-Soviet Union republics. It is located in Central Asia, and it becomes independent in 1991. Nowadays, the population is over 38 million. And one of the important things is we have more than about 1.4 million students in higher education. So maybe last 5 years, the demand to get the higher education is increased, and accordingly, we have so many new universities opened in Uzbekistan. So now I would like to continue with our ancestors, with which we are very proud of. And probably you know about the Khwarazmi, and because of him, the terminology algorithm appeared, and you know his work about the algebra. So he can be counted as one of the founders of algebra. And the last name is like a so-called the nickname Khwarazmi. He took from the region Khorasan, which is one of the regions nowadays, one of the 12 regions of Uzbekistan. He was born and grew in that region. So the next one is Alfraganus. He was famous in Europe in West as Alfraganus, but Alfarbani is also from one of that region, Fergana, of the recent Uzbekistan. So he's famous on calculation, distance, and size of planets, using the geometric and trigonometric reasonings, and also he's famous because of the construction of nilometer. It is still you can find in Egypt this nilometer to measure the water level in Nile. So the next one is Mirza Ulugh Beg. He was a ruler. He was a kind of grandson of the Tamerlan, who is one of the most famous empire builders. And he is also famous in astronomy, mainly in astronomy, but he has certain works on mathematics as well. We have many other scientists who lived and worked in the nowadays territory in Uzbekistan. Let us go to the modern development. So the Institute of Mathematics of the Uzbekistan Academy of Science has a name, named after the Romanowski, who is originally from Poland, but he was working in Tashkent in Uzbekistan, and he is a founder of this institute, and we are proud to have his name on our institute. And you can see the several the scholars, mathematicians. I just mentioned here the mathematicians, and they did a lot on the development of mathematics and also in organizing. Many of them were the president of Uzbekistan Academy of Sciences on certain time moments. And nowadays we have 7 academicians. It means that the full members of Academy of Sciences, they are mathematicians. And in our society, we have more than 100 full professors, more than 600 associate professors, which are members of our society and actively working in mathematics. So about the higher education, so we have more than 200 higher education institutions, so more than 100 universities, 30 international universities, and we have also the 5 academies, means that the Academy of Science, for example, the Uzbekistan Academy of Science one, and we have the other Academy of Sciences. So these academies also have certain research institutes. One of the main kind of core of the Uzbekistan mathematics is the Romanevsky Institute of Mathematics. So it has 5 ranges in different regions of Uzbekistan. And also we have certain universities where you can find actively working group of mathematicians. So here I mentioned some of them. So in different regions and also in Tashkent, and this is the new Uzbekistan University is newly established, but still actively growing. It might be the analog of Nazarbayev University in Kazakhstan. So now let me turn your attention to Uzbek Mathematical Society. And formally, it is founded in 1999. Now it is kind of non-government organization. It's kind of society. It's officially registered, and it follows all the regulation for non-government organizations. And in 2022, it becomes like a full member of IMU, International Mathematical Union. And you can find different research areas in which our Uzbek mathematicians are working. And also that this society is linked with the higher education, even the school education as well, because through the Institute of Mathematics, this society is responsible for revising all the textbooks, and also some monographs should be revised by the Institute of Mathematics or linked with our society. So all these textbooks and monographs in mathematics, which will be published in Uzbekistan, will be somehow linked with the Uzbek Mathematical Society. So here the officials of Uzbek Mathematical Society, the president is Professor Obidjon Zakirov. He's Dean of National University of Uzbekistan at the Faculty of Mathematics and Mechanics. And the vice president, the first vice president is Professor Ravshan Ashurov, who is of department in the Institute of Mathematics. And another vice president is Professor Abrar Khudoyberdiev. He's a deputy director of the Institute of Mathematics. He's more responsible for young researchers. And here we have members, and you can find here the academicians, like full members of Academy of Science, and professors, experienced professors, and more than 1,000 members. So you can count PhD students, master students. We have bachelor students also involved in this society. And we have some our representatives in international level. So you can find Uzbek professors working abroad in different universities in different countries. Especially now, young mathematicians, they are also continuing their career in international level. So we are expecting them to come back to Uzbekistan and develop further new directions, new scientific areas in mathematics. So our society is linked with different kind of journals in mathematics, especially these first 2 are founded by the Mathematical Society and Institute of Mathematics. So both of them are now indexed in Scopus. you can submit the papers on almost all areas of mathematics here. It's not specialized. So these are just linked with the universities. Some journals are linked with the universities, and also they are trying to improve their level and try to be covered in the Scopus. So here we have some partners. Our society is a member of Turkish World Mathematical Society, TWMS, and then we have an active partnership with the World Academy of Science. It's called TWAS, and we have here 4 full members of this academy. Nowadays, the Professor Ayupov is the president of Uzbekistan Academy of Science now. We have a young affiliates in TWAS as well. And we have also the special collaboration with USA. We have some already organized conference with California State University and in USA and in Uzbekistan as well. And also here, I would like to give information about degree. So we have still a double degree. So we have a PhD degree, Doctor of Philosophy, and also the Doctor of Science degree. It is the DSc, we call DSc. So it was maybe famous in the Soviet Union time. Nowadays, maybe in the world, we have only the small number of countries who is still keeping this two degree level. And also we have some students who defend in ICTP and in University of Santiago de Compostela in Spain, in Germany, Ruhr University of Bochum, in Italy, University of Pisa, and also we have ongoing the joint PhD program with Kent University and the Romanevsky Institute of Mathematics. It's already one PhD student got the double degree in 2022. So our members actively participating in international mathematical union activities like Congress, ICM, International Congress of Mathematicians. So in upcoming Congress, more than 10 members are already got the travel support. Probably half of them already got the visa. You know that nowadays to get a visa is also a problem. So probably they will participate actively in this upcoming Congress. So here we have a very close cooperation with IMU in SIMPA. So we have in Uzbekistan very good, very internationally recognized scientific school on algebra. So they are organizing these SIMPA schools. It was last one was last year in 2025. So it's already become like a regular manner. So we have also some women in mathematics. We have some already active female members who is active in international level as well. They are trying to organize some societies, and also they're trying to organize some special conferences. And I would like to know Dr. Umida Baltayeva, who is active in this direction. So we also have a very good government support. We have a presidential degrees related just with mathematics, especially with the Institute of Mathematics. And you can see here the consecutive 2 years, we have a special presidential degrees, and also the government trying to improve the financial support as well. And here we have a special fund of mathematics with 400,000 US dollars. And this fund will support some academic mobility of young mathematicians. And it is linked with the recommendation of Uzbek Mathematical Society. And also, I would like to talk about the international prize of the President of Uzbekistan. And this is named after Muhammad al-Khwarazmi. And this prize is in international level, and it will be awarded in 3 categories. Each one is 50,000 US dollars. So it's not awarded yet. We are still ongoing. So once it's started, then it will be probably the biannual. It's kind of biannual international prize. So we hope this will become famous among mathematicians as well. This is kind of special prize for mathematicians. And this is the short information about the Uzbek Mathematical Society, and we still need to work on the advertisement of this society in international level. So we would be happy if you will share this information among your colleagues. And welcome to Uzbekistan. So we will always happy to have you in Uzbekistan in different conferences. We have many conferences, but unfortunately not in the summertime. Usually we use in the summer is a vacation, really vacation, no conferences in summer. Thank you very much for your attention. So here are some contacts of the Uzbek Mathematical Society.
Thank you very much, Professor Karimov, for your words and providing us with all the context of the Uzbekistan Mathematical Society. It was very insightful. Thank you very much for accepting our invitation and collaborating with us. Now I'll ask Professor Duvan Cardona from ICMAM Latin America, from the Scientific Board, and also a board member of ISAAC, to share some words with us, please.
Okay, thank you very much, Manuel. Okay, I think I'm very happy to share some words, but first, personally, I'm happy with the organization of this conference because I very much appreciate both societies, so ISAAC, the International Society for Analysis, Applications, and Computations, and ICMAM Latin America, the international community of mathematicians from Latin America, where we are trying to promote mathematics in Latin America and cooperation of young researchers from Latin America with mathematicians worldwide, right? So that's why for us it's very important to have this series of conference with ISAAC in particular. I will mention later why ISAAC is very important in the history of ICMAM Latin America. So just on behalf of ICMAM Latin America, their attendees, let me begin by expressing my sincere gratitude to the distinguished authorities and representatives of the international mathematical associations that are joining us today. So in particular, I would like to express my gratitude to Professor Joachim Toff, to Professor Karin Deres-Hall, who I think is present also, to Professor Karina Navarro Gonzalez, who actually is the president of ICMAM Latin America, probably is not present, but of course, I work a lot in the organization of this conference and in other projects of ICMAM Latin America. So we also would like to express our deep appreciation to ISAAC. As we mentioned before, is the International Society for Analysis, its Applications and Computations, for the continuous and generous support. I could say that ISAAC was the first international society that support in name our society, our community, ICMAM, and that marked the beginning of many fruitful collaborations of ICMAM with other societies. So in particular, we strongly appreciate the support of Professor Awe Keller and Professor Paula Cerelleiras, right, for making this possible. So after the cooperation with ISAAC, following this, other organizations such as UMALCA, which is the Latin American Mathematical Union, have established joint activities with us. Also, we received twice funding from the International Mathematical Union for our initiatives. In particular, I also want to thank to the Ghent Analysis and PD Center. Of course, to his director, Professor Michael Ruchansky, who provided us with a framework to launch the series of books that we published in ICMAM Latin America with the Springer, related to analysis and partial differential equations, and that was that gave us also the opportunity to enter with cooperation with other editors in Springer, and it's a pleasure for us then to have for this year we are going to have a book series with the corresponding editors that will be experts in all the areas of mathematics and that are going to edit a series of books dedicated to providing a perspective of the mathematical research in Latin America, in the ICMAM Latin America series of books. So in many ways, I would say that this conference was inspired by the previous event organized by Professor Michael Ruchansky and Julio Delgado many years ago, I think more than 10 years ago. So it was in Imperial College. And there I had the opportunity to meet many of my current colleagues in Kazakhstan and Uzbekistan. So I want to express also my gratitude to our young colleagues, the young organizers of this conference, Manuel Martinez from Guatemala, Edison Lopez from Colombia, and Frederico Poku from Ghana, right? So the dedication of these mathematicians were, of course, essential to have the success of this conference. So in particular, this second edition of the ISAAC-ICMAM conference has benefited from the cooperation with the Romanowski Institute of Mathematics. So we have been delighted to welcome several researchers from Uzbekistan. We also have seen a strong participation from other regions, including India, and of course Latin America, and of which have greatly enriched our scientific program. Especially, I would like to thank to Erkin John Karimov for sharing our activities with his colleagues in Uzbekistan. So I could continue mentioning many things. I think it's a little bit late in Europe. I just want to express my gratitude then to all the attendees. Thank you very much for making this event a success, because it's because of the participants that are here that we organize this kind of scientific program. So thank you very much to all of you. Thank you very much, Professor Tov. I think we hear from you a very inspiring talk. I just make the comment to my team that is, of course, very, very inspiring to have one student of Anders Smelling, the Vickers School of Hormander, in particular, for us that we are very, of course, interested in pseudo-differential operators and doing research in Fourier integral operators. So thank you very much. Thank you very much to all the participants. And then I also, just to finish maybe my speech, you can see in the context of our conference and also in the cooperation with ICMAM Latin America, we have been a growing engagement of the African mathematical community in our activities. So in particular, we are supervising several African students, master and PhD levels, I will say. And now ICMAM Latin America has a strong cooperation with the African Institute of Mathematical Science in Ghana. So we are pleased to announce a new chapter of ICMAM, of our community, that is going to be called ICMAM Africa. ICMAM Africa. So it's my great pleasure to announce that one of our organizers, Dr. Frederico Poku, soon to be Dr. Frederico Poku, will serve as the president of this new initiative. So we are confident that under his leadership, ICMAM Africa will have many success to the African mathematical community. So soon we are going to have a dedicated website to share all the activities that we are going to have there. In particular, ICMAM Africa has been created as a project inside of ICMAM to promote mathematical research, collaboration, and visibility across the African continent. Our mission includes building a strong mathematical community in Africa, cooperating with the community of mathematicians in Latin America. We want to connect our researchers with the African continent. We want to promote the visibility of the African mathematical research, and then, of course, there to develop editorial and academic initiatives. So congratulations, Frederick, and we wish you a very success in this exciting new achievement in your career and this challenge that you are taking today.
Right. Thank you, Divan. In fact, I'm truly honored by this opportunity and excited to serve as the president of ICMAM Africa. I'm looking forward to working with the team and to make sure that this particular chapter will be a success. So the vision for this is to create a platform that fosters collaboration, innovation, and excellence in mathematics and its application, so that in the long way, we can drive a positive change in Africa. Thank you.
Thank you. I think we finished the program today then. Manuel, please continue.
Thank you very much, Duvan and Frederick. Thank you to each and every one of the attendees. It was a pleasure to have you with us today and the 2 days prior. I hope we can continue collaborating for many, many years forward. Thank you for presenting or attending the meetings. I think it was a great space for collaboration. Now, just to finish, perhaps if you wish, you can turn on your cameras for a final group picture for the ones that wish to appear in the picture. Okay, we'll give a couple of minutes so whoever wants to can turn their cameras on. Okay, so we'll take the picture in a minute, and with that we'll be concluding the 2026 ISAAC-ICMAM Analysis in Developing Countries Conference. Thank you very much. Hope to see you in the future.
Thank you very much. See you. Bye-bye.